Time is undoubtedly one of the most fundamental aspects of physics. It is the measure of change, the invisible framework that allows us to follow the universe, compare events, and define cause and effect. Unlike physical objects, time has no shape, weight, or consistency. It exists as a continuous progression that flows forward without pause. In essence, time provides structure to the universe. A second is defined by the vibrations of atoms, a day by Earth's rotation, and a year by its orbit around the Sun. These natural cycles give time a tangible presence that allows us to measure and organize reality. Without time, events would have no order and movement would not make sense. But time is more than a simple measure. It is a fundamental dimension of existence. It governs how processes unfold, from the movement of celestial bodies to the rhythms of biological life. Plants grow, tides change, and seasons follow one another, all following the passage of time. Position is the fundamental point of reference for movement. All objects exist somewhere in space, and describing their position is the first step to understanding movement. But position is not absolute. It is always measured in relation to something else. In physics, position is defined using a coordinate system. A simple number line can describe motion in one dimension, where moving forward increases position values and moving backward decreases them. In two dimensions, the coordinates on a map indicate exact locations. In three dimensions, objects move through space with x, y, and z coordinates that define their position at a given moment. But position is not just a location. It depends on the observer. A train passing through a station appears in different positions depending on whether you are inside the train or standing on the platform. This idea, known as a frame of reference, is crucial in physics. The same object can have different positions depending on the point of view, which influences how we measure movement. Position also plays a key role in navigation and measurement. Whether to track a satellite in orbit, locate the epicenter of an earthquake, or plot the movement of tectonic plates. Understanding position allows us to describe and predict how objects move in space. Distance is one of the most necessary concepts in physics, as it describes how far an object has traveled from one point to another. Unlike position, which specifies a location, distance is a purely length measure. It takes into account the total journey, regardless of direction. Let's imagine a car moving along a winding road. If it starts from one point, follows a curved route, and reaches another place, the distance traveled is the sum of all the segments of its journey. Even if the car returns to the starting point, the total distance is still the total length of the trip. Distance is a scalar quantity, which means it only has magnitude, not direction. This distinguishes it from displacement, which measures the shortest straight-line path between 2 points. For example, a person walking around a block may travel a great distance, but their displacement is only the direct separation between their starting and arrival points. In everyday life, distance is measured using units such as meters, kilometers, or miles, which helps us navigate roads, measure heights, and calculate depths. In science, precise distance measurements are essential for mapping microscopic structures, analyzing planetary motion, and even understanding the scale of the universe, from the smallest atomic interactions to the vast distances between galaxies. The concept of distance allows us to quantify movement and size, whether measuring the size of a room or the reach of a star. Distance serves as basis for understanding physical space and movement. Mass, one of the most fundamental aspects of physics, defines the presence of matter, giving everything from the smallest particles to the largest galaxies a measurable existence. Without mass, objects would have no substance, weight, or resistance to movement, fundamental traits that shape the physical world in essence. Mass quantifies how much matter an object contains and remains constant regardless of its location or external forces. A bowling ball is harder to lift than a tennis ball because it has more mass. Unlike weight, which depends on gravity, mass is an inherent property of an object that does not change, whether on Earth, on the Moon, or floating in deep space. Mass also determines how objects interact through gravitational attraction. The reason planets remain in orbit, things fall when released, and stars cluster together is due to mass. More massive objects exert stronger gravitational forces that influence everything from planetary motion to the structure of the universe. Mass is measured with balances or scales that compare an object's resistance to gravitational force in space, where there is no gravity. Mass is determined by the force required to accelerate an object. These measurements are crucial in physics, engineering, and even everyday activities, such as cooking or building. Mass is not just a number. It is the basis of all physical interactions. Dict's first step to unraveling the fundamental principles that govern the physical world. Movement is the basis of change in the universe, from the drift of galaxies to the displacement of a grain of sand. Nothing remains truly still, not even in the most static state. The atoms vibrate, the planets rotate, and space itself expands. Movement is not only displacement, it is the characteristic that defines existence. In its simplest form, movement is the change of an object's position over time relative to a chosen point of reference. A car that passes next to a still observer on the sidewalk is in movement, but for a passenger who is inside, it seems to be still. The movement of an object can only be described in comparison to something else. Movement is always relative. Each type of movement follows specific patterns. Some movements are uniform, in which an object moves at a constant speed along a straight trajectory. Other movements are non-uniform, in which the speed or direction changes with time. The swing of a pendulum, the orbit of the moon, or the rise and fall of the oceanic tides all are forms of movement molded by the forces that act on them. Movement can be linear, like a falling rock, or circular, like a turning wheel. It can be periodic, like the swing of a clock's pendulum, or chaotic, like the erratic movement of molecules in a gas. Regardless of its form, movement governs how objects interact, how energy transfers, and how systems evolve over time. Understanding movement is essential to understanding the physical world, since it dictates the patterns of nature, from the simplest fall of a leaf to the vast movements of the celestial bodies. Recognizing and analyzing movement is the first step to exploring the deepest principles that define the mechanics of the universe. Speed measures how quickly something moves from one place to another. It is the rate at which a distance is traveled in a determined time, making it one of the most fundamental aspects of movement. Whether it is a car circulating on a road, a person running, or sound moving through the air, speed describes how quickly an object is in motion. In essence, speed is simply the total distance traveled divided by the time taken. If a train travels 200 kilometers in 4 hours, its average speed is 50 kilometers per hour. Since speed only tells us how fast something moves, not in what direction, it is classified as a scalar quantity. Speed is present in all aspects of daily life. Walking calmly, a person moves at about 5 kilometers per hour. An airplane flies through the sky at almost 900 kilometers per hour. The fastest terrestrial animal, the cheetah, can reach speeds of more than 100 kilometers per hour, but even these are slow in comparison with astronomical speeds. The Earth orbits around the Sun at about 107,000 kilometers per hour, and light travels at almost 300,000 kilometers per second. Understanding speed allows us to measure, compare, and predict movement in everything from transport to natural phenomena. It helps engineers design faster vehicles, scientists study movement in physics, and astronomers calculate distances in space. Whether it is about measuring the rhythm of daily activities or tracking objects that move on a cosmic scale, speed is an essential concept that defines how things move through the world. Velocity is more than just speed, it is speed with direction. While speed measures how fast something moves, velocity specifies both the speed and the direction. This distinction makes velocity a vector quantity, which means that it has magnitude and direction. Let's imagine a car moving at 60 kilometers per hour. If it travels towards the east, its velocity is 60 kilometers per hour eastward. If it turns towards the west at the same speed, the velocity changes, not because the speed has changed, but because the direction has changed. This makes velocity a more complete description of movement than speed alone. In daily life, velocity helps describe movement with greater precision. An airplane that flies at 800 kilometers per hour is not only moving, but it has a velocity based on its direction. The wind velocity determines whether a flight is delayed or arrives ahead of time. Oceanic currents influence boats based on their velocity. Even in sports, understanding velocity is fundamental, whether it is to follow the trajectory of a baseball or calculate the trajectory of a soccer ball. In physics, velocity is essential to describe movement at all scales. It defines how objects move, how trajectories are calculated, and how movement is predicted, whether it is to follow planetary orbits, measure the flow of fluids, or study particles in motion. Velocity allows a precise analysis of movement when knowing both the speed and the direction. Velocity provides a complete picture of how objects move through space and constitutes the basis for understanding movement in mechanics, navigation, and even astrophysics, making it one of physics' most fundamental concepts. Acceleration describes how movement changes. Whether a car accelerates, brakes, or turns a corner, it is experiencing acceleration. Unlike speed, which measures how fast something moves, or velocity, which adds the direction, acceleration measures how quickly the velocity changes. In essence, acceleration is the rate of change of velocity over time. If a car moves at 20 meters per second and increases to 30 meters per second in 5 seconds, it has an acceleration of 2 meters per second squared. But acceleration is not only about accelerating, but it also includes deceleration, known as slowing down, and changes of direction. A car that turns at constant speed continues accelerating because its velocity is changing. Acceleration is a key concept to describe how objects move, from daily activities to astronomical phenomena. When you push a bicycle, the increase in speed is acceleration. The jolt you feel in an elevator when it starts or stops is acceleration. Even the Earth accelerates when following its curved orbit around the Sun. Gravity is one of the best-known sources of acceleration. Any object that falls freely near Earth's surface accelerates to 98 meters per square second, regardless of its mass. This explains why two objects dropped from the same height fall at the same speed, assuming air resistance is negligible. Whether following a moving vehicle, studying falling objects, or analyzing planetary motion, acceleration provides a fundamental way to describe and predict changes in motion. Understanding acceleration allows us to analyze motion precisely, which makes it an essential concept in physics. Force. Nothing moves, stops, or changes without force. It is the invisible hand behind every movement, from a falling raindrop to the motion of the enormous tectonic plates. Without force, the world would be static. There would be no rivers flowing, no clouds moving, or movement of objects. In essence, force is simply an interaction causing a change in motion. It can cause something to start moving, stop, or change its direction. A force applied to an object can accelerate or decelerate it. The more force exerted, the greater the effect. Pushing an empty cart is easy, but a loaded one requires more effort. This is because greater mass requires greater force to achieve the same movement. Forces come in many forms. Contact forces require physical interaction, such as friction or applied force. Try sliding a book across a table. Friction opposes the movement and slows it down. Push a door, and it moves in response to the applied force. Forces can be balanced or unbalanced. When equal forces act in opposite directions, there is no movement, such as when two people push each other with equal force. But when the forces are unbalanced, movement occurs. The stronger force overcomes the weaker one, putting objects in motion or altering their speed, from the pull of a stretched rubber band to the impact of a hammer hitting a nail. Every action is governed by force, whether subtle or immense. Force is the reason why objects move, interact, and respond to their environment, which makes it one of the most fundamental principles of physics, inertia. This plays a crucial role in shaping everything from everyday experiences to large-scale cosmic interactions. It is the reason why a bicycle stays upright when it moves, but falls when it is stopped, why astronauts in space continue to float without resistance, and why heavier objects require more effort to move or stop. Inertia is not only a property of objects, it is a fundamental characteristic of matter itself. Engineers and scientists depend on inertia to design safer vehicles, stable bridges, and efficient machinery. The crumple zones of automobiles are built to counteract inertia during a crash, absorbing the impact forces to reduce damage. In sports, understanding inertia helps athletes control movement, whether a runner maintaining momentum or a gymnast landing. Even in space exploration, spacecraft must account for inertia using precise impulses to adjust course, since objects in the vacuum continue to move indefinitely without external resistance. On a larger scale, inertia governs planetary motion. Earth orbits the Sun not because it is actively propelled, but because inertia keeps it in motion while gravity curves its trajectory into an orbit. The same principle applies to galaxies, where vast celestial bodies move in predictable patterns due to their inertia. Recognizing inertia allows us to predict movement, control forces effectively, and innovate in fields from transportation to astrophysics. Whether it is the stability of buildings, the efficiency of machines, or the mechanics of movement, inertia is a silent but ever-present force shaping the physical world. Momentum is why a moving train takes kilometers to stop, why a bullet can pierce steel, and why catching a fast-moving ball hurts your hand. It is not just movement, but movement with impact. Momentum is the product of the mass and the speed of an object mass and the speed of an object. The greater the mass or speed, the greater the momentum. That is why a truck moving slowly can have more momentum than a bicycle going at full speed. It all comes down to the combination of mass and movement. Momentum is also a vector quantity, meaning it has magnitude and direction. A car moving east at 60 miles per hour has momentum in that direction. If it changes speed or direction, its momentum also changes. One of physics' most fundamental principles is the conservation of momentum in a closed system. Momentum is never lost. It is only transferred. That is why, in collisions, the total momentum before impact equals the total momentum after. In elastic collisions, such as two billiard balls colliding, momentum is transferred with minimal energy loss. In inelastic collisions, such as a car accident, part of the momentum is converted into sound, heat, or deformation. Momentum also plays an important role in space travel, since there is no air resistance there. Astronauts depend on the conservation of momentum to maneuver and push an object in one direction and move in the opposite direction. Impulse governs how objects interact, transfer energy, and move until something stops them. Consider the impulse of a boxer receiving a punch, a baseball bat hitting a ball, or a car airbag inflating. Each of these instances is governed by impulse, the force that changes an object's momentum. Impulse is the product of force and the time during which the force acts. When a force acts on an object, it changes its momentum. The longer a force is applied, the greater the change will be. This relationship is summarized by the equation: impulse equals force times time. Imagine you kick a soccer ball. A quick hit makes it roll slowly, but a strong, sustained kick throws it to the other side of the field. The difference: more impulse, a greater force for longer, transfers more momentum. Impulse also explains how safety mechanisms function. A car accident can be fatal, but airbags and crumple zones prolong the time during which the collision occurs, reducing the force experienced by passengers. Instead of an abrupt stop, gradual deceleration distributes the impulse, reducing injuries. In sports, impulse determines performance. A golfer follows through on the swing to maintain contact with the ball for longer, maximizing impulse and distance. A baseball player catches a ball moving quickly by pulling the glove back at the moment of impact, prolonging the time and reducing the force on the hand. Impulse is everywhere, from car shocks to how we land after a jump. Impulse shapes movement, impact, and safety. It is the hidden factor behind each collision, each acceleration, and each reaction in fractions of a second that alters the impulse in the real world. Newton's laws are the basis of classical physics, governing how objects move and interact with forces. These three simple but profound principles explain everything from the flight of rockets to the way you push a door to open it. The first law, often called the law of inertia, states that an object at rest remains at rest, and an object in motion remains in motion unless acted upon by an external force. Imagine a book on a table. It will not move unless you push it. Similarly, a moving car does not stop instantaneously when the brakes are applied, but resists the change in motion as a result of inertia. The second law defines the relationship between force, mass, and acceleration. Force equals mass times acceleration. This means the more you push an object, the faster it accelerates. However, a heavier object needs more force to reach the same acceleration. That is why kicking a soccer ball sends it flying, but kicking a bowling ball barely moves it. This law is key to understanding how everything works, from bicycles to spaceships. The third law is often summarized as, for every action, there is an equal and opposite reaction. When you jump from a boat, you push the boat back while propelling yourself forward. Rockets work in the same way. By expelling exhaust gases downwards, they generate upward thrust. Together, these three laws explain movement in almost every situation, from predicting planetary orbits to designing high-speed trains. These new principles remain indispensable, as they are pillars of physics and provide a framework for understanding force, motion, and interaction in the physical world. Gravity is the silent architect of the universe. It keeps the planets in orbit, shapes galaxies, and keeps everything together, including you, who are currently pressing against the ground. Without gravity, the Earth as we know it would not exist, nor the atmosphere, nor the oceans, nor the stars. It is the force that governs structure and movement at all scales. At its most basic, gravity is the attraction between two objects with mass. The greater the mass, the greater the attractive force. That is why the Earth's gravity keeps the moon in orbit, while the sun's immense gravity keeps the planets in place. The sun's immense gravity keeps the planets in place. Newton's law of universal gravitation states that every mass exerts a force on all other masses, and that this force weakens with distance. But Newton's explanation was only part of the story. Einstein's theory of general relativity redefined gravity as the curvature of space-time. Imagine placing a heavy ball on a stretched rubber sheet. The surface curve around it, and a smaller ball placed nearby will roll towards the indentation, just as a planet orbits a star, following the curved path created by its mass. That is why gravity is not just a force. It is the shape of reality. Gravity is not only used to keep things in place, but it also determines how time flows. Stronger gravitational fields, like those near black holes, slow down time relative to weaker ones. This effect, known as gravitational time dilation, has been confirmed by atomic clocks and satellites, which mark time slightly faster than those on Earth. Every movement in the universe, from the fall of objects to the expansion of the cosmos, is determined by gravity. It is both familiar and mysterious, attracting everything to everything in an endless cosmic dance. Free fall is movement in its purest form, an object moving under the influence of gravity without resistance or interference, whether it is a parachutist jumping from a plane or an apple falling from a tree. Free fall is the simplest demonstration of gravity in action in a vacuum where there is no air resistance. All objects, regardless of mass, fall at the same rate. This was famously demonstrated by Galileo at the Leaning Tower of Pisa and later confirmed on the moon when an astronaut dropped a feather and a hammer, which impacted the surface simultaneously. The acceleration due to gravity on Earth is about 98 meters per second squared, which means that every second an object in free fall increases its speed by 98 m/s. Free fall refers not only to objects that fall to the ground, but extends to celestial mechanics. The moon, technically, is in perpetual free fall around the Earth, but its movement curves into an orbit instead of descending in a straight line. Satellites also constantly fall toward the Earth, but their forward speed keeps them in orbit instead of crashing. Even when you experience weightlessness, such as in space or during a zero-gravity flight, you are still in free fall, falling at the same rate as your surroundings. That is why astronauts seem to float. They're not defying gravity. They're simply in a state in which gravity is the only acting force. Free fall reveals the fundamental nature of gravitational motion: universal, inevitable, and independent of an object's properties, whether as light as a feather or as heavy as a rock. If gravity is the only force acting, the rules are the same. Friction is the invisible force that slows movement, where surfaces and prevents objects from sliding endlessly. Without it, walking would be impossible, cars would not stop, and nails would not hold the wood. It is both an obstacle to movement and a necessity to control. In essence, friction happens when two surfaces come into contact, resisting their relative movement between each other. Even the smoothest materials have microscopic irregularities, and when pressed together, these small bumps interlock, creating resistance. The rougher the surface, the greater the friction is. There are two main types: static and kinetic friction. Static friction keeps objects at rest. Imagine trying to push a heavy box. At first, it does not move because static friction resists your effort. Once you push hard enough, the box begins to slide, moving to kinetic friction, which is weaker but still slows movement. That is why it takes more effort to start an object moving than to keep it moving. Friction also depends on the normal force, the force that presses two surfaces together. Therefore, a heavier object that presses harder experiences greater friction. However, friction does not depend on the area. A wide and a narrow tire on the same road experience approximately the same friction, since the key factor is the distribution of force, not the contact area. Friction is everywhere. It allows brakes to stop vehicles, athletes to grip surfaces, and even generates heat when you rub your hands together. Engineers work to reduce friction in machines using lubricants, while athletes and drivers look for ways to increase it for better control, whether to slow movement or allow it. Friction governs how objects interact with their environment, making it one of the most fundamental forces in daily life. Air resistance. Not all falling objects follow the simple rules of free fall. If we drop a stone and a feather, the stone will reach the ground first, not because it is heavier, but because of air resistance, the force that opposes movement through air. This invisible force can slow objects, shape flight paths, and even allow human beings to glide through the sky. Air resistance, or drag, occurs because air is made up of molecules, and when an object moves, it must push these molecules aside. The faster it moves, the more collisions occur, which increases the resistance. That is why cyclists lean forward to reduce resistance, and parachutes expand to maximize it. The effect of air resistance depends on speed, shape, and surface area. An aerodynamic object, such as a bullet, passes through the air with minimal resistance, while a wide parachute creates significant resistance that slows the descent. This force is the reason why skydivers fall rapidly at first, but then stabilize at terminal velocity, the point at which gravity and air resistance balance, preventing further acceleration. Without air resistance, objects fall at the same speed as in a vacuum on Earth. However, it plays a crucial role in everything from weather patterns to vehicle design. Airplanes depend on controlled air resistance to lift off, while meteorites burn up due to extreme friction with the atmosphere. Work in physics is not about effort, but about energy that is transferred. Every time you push, pull, or lift an object, you're doing work by applying a force that moves something across a distance. If there is no movement, no matter how much effort is applied, no work is done. Imagine pushing against a wall with all your might. You may feel exhausted, but if the wall does not move, no work has been done in the physical sense. Work only occurs when force causes a displacement, such as lifting a book from the floor and placing it on a shelf, kicking a ball, or pedaling a bicycle. The amount of work done depends on both the force applied and the distance traveled. Lifting a heavy box to a high shelf requires more work than lifting a lighter box to the same height. Similarly, moving an object a greater distance increases the work done. Work also depends on the direction. If the force is applied in the same direction as the movement, such as pulling a cart forward, all the energy goes into the work. But if the force is applied at an angle, such as pushing a box diagonally, only part of the effort contributes to the movement. The work is crucial to understanding how energy flows through systems. It explains how engines work, how machines operate, even how the human body moves. When a work is done, the energy is transferred, which allows the systems to function. From the functioning of enormous industrial machines to something as simple as throwing a ball, each movement, each action that transfers energy from one form to another is work and movement. It is the fundamental link between force and energy that drives the mechanics of the physical world. Energy is the currency of the universe. It feeds each movement, each transformation, each force at play. From the heat of the sun to the movement of your body, energy is what makes everything happen. In essence, energy is the capacity to do work. It exists in many forms. Kinetic energy in objects and movement, potential energy stored in stretched springs or elevated masses, thermal energy in heat, and chemical energy in foods and fuels. Although energy constantly changes form, it is never created nor destroyed. This fundamental truth is known as the law of conservation of energy. Energy can be transferred or transformed, but the total amount in a closed system remains constant. Think of a roller coaster at the top of its journey. It has maximum gravitational potential energy, but as it descends, that stored energy is transformed into kinetic energy, accelerating the roller coaster. Friction and air resistance convert part of that energy into heat, but no energy disappears. It simply passes from one form to another. Even the foods that we eat follow this rule. The chemical energy of the foods is converted into kinetic energy for the movement, into thermal energy to maintain the body temperature, and into electrical energy that feeds the nerve signals. The energy feeds all the systems, from the microscopic atoms to the vast galaxies. Nuclear reactions convert masses into energy that feeds the sun. Electric currents move through circuits, illuminating entire cities. Even life itself depends on the energy stored in molecules and released to maintain the functioning of organisms. Everything in physics, from movement to forces, is connected to energy. It determines how objects move, how they collide, and how they change, whether it is an apple falling or a star being born. Energy is the thread that unites the universe, giving form to reality itself. Kinetic energy. Kinetic energy is the energy of movement. Anything that moves carries it, whether it is a raindrop falling, a bullet flying, or a planet rushing through space. Kinetic energy is what gives power to movement. The amount of kinetic energy an object has depends on two factors: mass and speed. A heavier object has more kinetic energy than a lighter one moving at the same speed, but speed plays an even more important role. When something moves twice as fast, its kinetic energy increases much more than double. For that reason, a small stone moving at great speed can cause damage, while an enormous immobile rock does not have any kinetic energy. Think of a car accident. A car moving slowly can dent a bumper, but one moving at great speed can cause total destruction. The faster an object moves, the greater is the energy that it transports, and the greater is the impact that it can have. For that reason, professional athletes compete in racing cars, and even space shuttles are designed paying special attention to movement. Taking advantage of kinetic energy can make the difference between efficiency and failure. Kinetic energy does not only apply to objects we can see, but it even exists at a microscopic level in the movement of molecules. The greater its kinetic energy, the hotter a substance becomes. For that reason, friction produces heat. When rubbing your hands, the movement of the molecules is increased, generating heat. Kinetic energy is everywhere, from a movement of the smallest atoms to the largest celestial bodies. Understanding it helps explain everything, from the mechanics of machines to the forces that give form to the universe. Potential energy. Energy does not always have to be in movement to exist. Part of the energy remains stored, waiting for the right moment to be released. This is potential energy, the energy an object possesses due to its position or condition, whether it is a stretched elastic band, a compressed spring, or water behind a dam. Potential energy is ready to transform into movement when the adequate force acts on it. One of the best-known forms is gravitational potential energy. A rock at the edge of a cliff does not move, but it contains energy due to its height. The higher the rock is, the more potential energy it has. Once it falls, that stored energy is converted into kinetic energy, driving its descent. Elastic potential energy works in a similar way. A slingshot stretched backwards contains energy in its tension. When released, that energy drives an object forward. Springs work in the same way. Whether compressed or stretched, they store energy that is released when they return to their original form. Chemical potential energy exists at a molecular level. The foods we eat, the fuel of a car, or even explosives contain energy stored in their chemical bonds. When activated, this energy is released in the form of movement, heat, or combustion. The potential energy allows to store the energy and use it precisely when it is needed, driving everything from hydroelectric dams to the muscular movement. Recognizing its role helps to explain how forces accumulate and how movement is controlled, shaping interactions from microscopic processes to the most powerful forces in the universe. Energy is not only force. It is the rate at which work gets done. It measures the speed at which energy is transferred or converted, determining the efficiency with which something goes from one state to another, whether it is a sprinter shooting out of the starting blocks or an engine powering a car. Power determines the rate of energy use. Let's imagine two people climbing a flight of stairs. One takes their time and climbs with a steady step, while the other runs up in seconds. Both do the same work, since they raise their body weight to the same height, but the second person exerts more power because they complete the task in less time. Power is not only effort, it is speed. This concept applies everywhere. A high-powered car accelerates faster because it transmits energy to the wheels more quickly. A light bulb with more power illuminates more because it converts electrical energy into light at a faster rate. Even in nature, a roaring waterfall generates immense power as water crashes against the rocks, rapidly transferring energy to them. Power also determines efficiency. A machine completing a task quickly with less wasted energy is more powerful than one that struggles and takes longer. That is why power is important, from the watts of a light bulb to the horsepower of an engine, since they indicate how effectively energy is used. In essence, power has to do with the control of energy, not only with brute force, but with the efficiency and speed with which energy flows from the smallest circuits to the largest industrial systems. Power drives the modern world, shaping everything from technology to transportation and converting potential into action in an instantaneous conservation of energy. Energy never disappears, it only changes form. This is the principle of the conservation of energy, a most fundamental law of physics. Whatever happens, the total energy in a closed system remains constant. It cannot be created or destroyed, only transformed. Imagine a roller coaster at its highest point. At that moment, it contains energy in the form of potential energy stored due to its height. As it begins its descent, that energy transforms into kinetic energy, the energy of movement. The faster it moves, the more kinetic energy it has, but the total energy, potential plus kinetic, remains unchanged. Not even friction and air resistance destroy energy. They simply convert part of it into heat. This principle applies to everything around us. A swinging pendulum moves back and forth, exchanging potential and kinetic energy with each oscillation, until air resistance gradually converts some of that energy into heat. The fuel in a car contains chemical energy that is converted into movement, sound, and heat when the engine runs. Even the food we eat follows this rule. Our bodies convert chemical energy into movement, heat, and biological processes. The conservation of energy governs everything, from the smallest atomic reactions to the largest cosmic events. The events the stars burn by converting nuclear energy into light and heat, and even the expansion of the universe obeys the principles of conservation of energy. This law establishes a limit for what is possible in physics. It tells us that no machine can create more energy than it consumes, and that no event in nature occurs without energy transformation. Energy moves, changes, and flows, but never disappears. Understanding this law is not only a matter of physics, but of seeing the hidden exchanges that drive the universe itself. Conservation of momentum. Momentum never disappears, it only changes. This is the principle of conservation of momentum, a fundamental law of physics stating that, in a closed system, the total momentum remains constant unless an external force acts on it. It governs everything from the movement of planets to collisions on a pool table. Momentum is the product of an object's mass and velocity. The larger or faster something moves, the more momentum it has. But what makes this principle so powerful is that momentum is not only something an object has, it is something that must be conserved. When two objects interact, they exchange momentum, but the total amount remains unchanged. Let's consider a simple collision. If two ice skaters push each other, they move in opposite directions. Although each skater changes speed, the total momentum before and after the push remains the same. The movement of one is perfectly balanced by the movement of the other. This principle applies to all scales of space where there is no friction. An astronaut who throws an object in one direction will move in the opposite direction. Rockets work according to this same principle. By expelling fuel at high speed, they propel themselves forward. Even high-speed crashes follow this rule. In car collisions, momentum is redistributed between vehicles, with energy dissipated as sound, heat, and deformation. The conservation of momentum is absolute, underlies Newton's laws, and even extends to quantum mechanics. Every movement, every impact, every change follows this unbreakable law. However chaotic the system may seem, its total momentum remains the same. It is nature's way of ensuring perfect balance. Work and energy theorem. Energy does not appear out of nowhere. It comes from work. This is the basis of the work and energy theorem, which states that the work done on an object translates directly into a change in its energy, whether accelerating a car, lifting a weight, or stopping a moving object. Work and energy are two sides of the same equation. To understand it, imagine pushing a heavy box across the floor. The more you push, the faster it moves. That effort, the force you apply over a distance, is work, and the result is that the box gains kinetic energy. The more work you do, the more energy the box gains. Now think about stepping on the brake of a moving car. The friction between the tires and the road does negative work, reduces the kinetic energy of the car until it stops. Work not only increases energy, it can also take energy away. This relationship extends beyond simple movement. When you lift an object against gravity, you do work against the force that pulls it down. That work is stored as potential energy, ready to be released when the object falls. If you drop it, that stored energy turns back into movement. The work and energy theorem connects force, motion, and energy into a single principle. Whenever a force acts over a distance, it transfers energy. This concept explains everything from engines that generate energy to how athletes gain momentum. Without work, there is no change in energy. That's why the work and energy theorem is a cornerstone of physics. It reveals that energy is not just a property, but something that must be transferred through action. Every movement, every applied force, every change in speed or height is work that shapes energy and fuels the mechanics of the universe. Balance of the center of mass. Balance a pencil on your finger, and you will quickly find a single point where it remains stable. That point is its center of mass, the average position of all the object's mass. It is the point at which an object behaves as if all its mass were concentrated, making it essential for understanding movement, stability, and balance. All objects have a center of mass, whether it is a simple ruler or a complex system like the human body. If you throw a wrench into the air, its individual parts may rotate unpredictably, but its center of mass follows a smooth, predictable path. This principle is the reason why athletes, dancers, and engineers depend on their understanding. Whether it is a gymnast who adjusts in the air, a rocket that maintains stability, or a vehicle that remains upright during a turn. The center of mass does not have to be inside the object. A hollow ring, for example, has its center of mass at the geometric center, where there is no actual material. In human beings, it moves with posture and movement. Standing is near the belly, but if we lean forward, it also moves forward. This concept is fundamental in physics and engineering. In architecture, buildings are designed with a low center of mass to ensure stability. In space travel, rockets must have the center of mass carefully aligned to ensure controlled movement. Understanding the center of mass helps explain why objects tip over, how forces act on a system, and how motion remains stable or chaotic. It is the invisible anchor of movement that defines how things balance, rotate, and move through space. Whether designing machines, predicting planetary orbits, or simply walking without falling, it all depends on this fundamental principle, the center of gravity and balance. Pencil on your finger, and there's only one point where it will not fall. That point is its center of gravity, the location where the weight of an object is perfectly balanced in all directions. Whether it's a spinning gymnast, a skyscraper, or a moving car, the center of gravity determines stability and movement. The center of gravity, CG, is the average location of the weight distribution of an object. In symmetrical objects, such as a sphere or a cube, the CG is located in the geometric center, but in irregular shapes it shifts depending on how the mass is distributed. For example, a hammer has its CG closer to the heavy metal head than to the lighter handle. In everyday life, stability depends on the center of gravity. A low CG makes objects more difficult to tip over, so racing cars stick to the ground and wide-base structures, like pyramids, remain standing for centuries. When the CG shifts beyond the base of support of an object, it falls. That is why walkers with narrow RPPs carry long sticks to lower their CG and maintain balance in human movement. The CG is constantly changing when you're standing, since the waist when you lean forward shifts outward, which increases the risk of falls. Athletes and artists train to control their center of gravity in order to improve their performance. Sprinters lean forward to shift their center of gravity forward, and ballet dancers adjust their limbs to maintain balance in the air. Engineers, architects, and designers rely on the principles of the center of gravity to ensure safety and performance. From building bridges to designing backpacks that seem lighter, understanding the center of gravity is fundamental to mastering balance, stability, and control in the physical world. Rotational movement. Imagine spinning the wheel of a bicycle. The faster it spins, the harder it is to stop it. This is rotational movement, the physics of objects that spin, rotate, and roll. Unlike linear motion, in which objects move in a straight line, rotational motion describes motion around a fixed axis. In essence, rotational motion follows many of the same principles as linear motion, but with a twist, literally. Instead of position, we use angular displacement to describe how much something has rotated. Instead of speed, we use angular velocity, which tells us how fast it is spinning. And instead of force, we use torque, which measures how effectively a force can cause rotation. If you have ever tried to open a door that resists, you will instinctively know that it is easier to push near the edge than near the hinge. That is torque in action, the force applied at a distance from the pivot point. A key idea in rotary motion is the moment of inertia, which is like rotational mass. An artistic skater illustrates this perfectly. When retracting their arms, they spin faster, and when extending them, they slow down. This is because their moment of inertia changes as mass is redistributed closer or further from the axis of rotation. Rotary motion is everywhere. The Earth rotates on its axis, creating day and night. The planets orbit stars due to the interaction of rotation and gravity. Even machines, from car engines to wind turbines, rely on rotary dynamics principles. By understanding rotary motion, we unveil the mechanics behind countless natural and artificial systems. It connects everyday experiences with the fundamental forces shaping our world, revealing how rotating objects behave predictably and profoundly. Moment of inertia. Imagine you're trying to turn a door by pushing near the hinges instead of pushing on the edge. The difference in effort you feel is due to the moment of inertia, the rotational counterpart of mass and motion. It determines an object's resistance to changes in rotation. The moment of inertia depends on two factors: the mass of an object and how that mass is distributed in relation to the axis of rotation. The further the mass is from the axis, the greater the inertia. That is why an artistic skater can spin faster by bringing their arms together, since by reducing the distribution of mass, the moment of inertia decreases, which allows the rotation to accelerate. Different shapes have different moments of inertia. A solid sphere rotates more easily than a hollow one of the same mass and radius because more mass is concentrated closer to the center. Similarly, a long bar rotating about its center rotates more easily than the same bar rotating about one end. Understanding moment of inertia is fundamental in engineering and physics. In vehicles, flywheels store rotational energy by maximizing inertia and stabilizing movement. In sports, athletes adjust their body position to control turns in gymnastics or jumping. Even celestial bodies, such as planets and stars, follow these principles in their rotational dynamics. The moment of inertia explains why some objects rotate easily while others resist. It governs everything from simple mechanical systems to the rotation of galaxies, controlling mass distribution. We manipulate rotational motion by applying the same fundamental physical principles, whether spinning a wheel, designing machinery, or launching spacecraft. Torque. Imagine you're trying to open a very heavy door. The force you apply matters. If you push near the hinges, the door barely moves. If you push on the edge, it opens easily. This is torque, the rotational equivalent of force. It determines how effectively a force can rotate an object around an axis. Torque depends on three factors: the amount of force applied, the distance from the pivot, and the angle at which the force is applied. The further you push from the axis, the greater the effect. That is why wrenches have long handles. A greater distance from the pivot means more torque with the same effort. If the force is applied at an angle, only the component perpendicular to the lever arm contributes to the rotation. A classic example of torque in action is a seesaw. If two people of the same weight sit at the same distance from the center, equilibrium is maintained, but if one gets closer, their torque decreases, causing the other side to tilt. Torque explains how levers work, from hammer levers to bicycle pedals, amplifying small forces into powerful effects. In the natural world, torque governs the movement of planets, the rotation of gears, and the stability of bridges. Engineers rely on torque calculations to design everything from automobile engines to wind turbines, ensuring structures withstand rotational forces without failure. Understanding torque is key to mastering rotational motion, whether opening a door, tightening a screw, or designing machinery. Torque is the invisible force that dictates how things rotate, pivot, and move. It unites everyday experiences with the deeper mechanics of physics, making the world's movement not only predictable, but also controllable. Imagine an artistic skater spinning on the ice while bringing their arms together. They spin faster without any external push. This is angular momentum in action, a fundamental principle governing all rotating objects, from spinning tops to planets orbiting the sun. Angular momentum is the rotational equivalent of linear momentum. An object in motion remains in motion unless acted upon by an external force. Similarly, in rotational motion, an object continues to rotate unless acted upon by an external torque. The key factors that determine angular momentum are the mass of an object, its angular velocity, and how that mass is distributed in relation to the axis of rotation. The most striking characteristic of angular momentum is its conservation. Unless an external torque interferes, angular momentum remains constant. This explains why a spinning skater accelerates when they bring their arms together. By reducing the distribution of mass around the axis, the speed of rotation increases to compensate. The same principle applies to planets. When they approach the sun, they accelerate, and when they move away, they slow down. Angular momentum plays a crucial role in engineering, space exploration, and even nature. The gyroscopes, which are based on angular momentum, help to stabilize ships, airplanes, and even smartphones. In space, astronauts use them to maneuver spacecraft without external forces. Understanding angular momentum reveals why rotating objects behave as they do, from a child's toy spinning on a table to the formation of galaxies. It is a concept connecting the smallest systems with the largest, demonstrating that movement, once initiated, follows precise and immutable laws. The conservation of angular momentum. A figure skater spins elegantly on the ice with arms outstretched, then brings them together and spins faster. No external force acted on her, but her rotational speed changed. This is the conservation of angular momentum, a principle governing rotational motion. Angular momentum is the rotational equivalent of linear momentum. It describes how an object moves in a circular path. The key idea is that if no external torque acts on a system, its angular momentum remains constant. This means that if one part of the system changes, such as a skater bringing her arms together, the other part, in this case the speed of rotation, must adjust to compensate. Mathematically, angular momentum depends on an object's moment of inertia, its resistance to rotation, and its angular velocity or rotational speed. When the skater brings her arms together, she reduces her moment of inertia, which makes rotation easier to conserve angular momentum. So her rotational speed must increase. This principle extends far beyond ice rinks. In space, where no external forces such as friction act, it governs everything from planets to galaxies. When a collapsing star shrinks, its moment of inertia decreases, causing it to spin rapidly, sometimes forming a neutron star spinning hundreds of times per second. Even everyday objects obey this law. A swivel chair, a fidget spinner, or a bicycle wheel all demonstrate the conservation of angular momentum. Engineers use this principle in spacecraft design, adjusting the rotation without thrusters by displacing the mass inside. The conservation of angular momentum ensures that, in any isolated system, rotation persists unless an external force acts, whether in sports, astrophysics, or engineering. Understanding this principle allows us to delve deeper into how the universe moves. Centripetal force. Imagine swinging a ball tied to a rope in a circle. The ball does not shoot outward, but follows its curved path. The force that keeps it in motion does not pull outward, but inward. This inward force is known as centripetal force and is essential for any object moving along a circular path. The centripetal force acts perpendicularly to the object's motion, constantly pulling toward the center of rotation. Without it, the object would move in a straight line due to inertia. Think of a car turning on a curve. The friction between the tires and the road provides the centripetal force, preventing the car from skidding. If the road were icy and the friction decreased, the car would have difficulty staying on course. In its curved path, in planetary motion, gravity acts as centripetal force, keeping planets in orbit around the sun instead of shooting into space. The Earth's motion is continuously redirected inward due to the sun's gravitational pull. Similarly, the moon remains in orbit around the Earth thanks to this principle. The strength of the centripetal force depends on three factors: the object's mass, its velocity, and the radius of the circular path. A heavier object or higher speed requires a greater inward force to maintain circular motion. Similarly, decreasing the radius, such as pulling a spinning skater's arms inward, requires a stronger force. Centripetal force is everywhere, from the curves of race tracks to the orbits of galaxies, whether in engineering, sports, or celestial mechanics. Controlling this force is key to maintaining both stability and movement. It is what keeps satellites in orbit, roller coasters on tracks, and planets in their cosmic dance. Simple machines lift a heavy object, open a door, or even cut paper. These everyday actions depend on simple machines, fundamental devices that facilitate work by amplifying force or changing direction. Despite their simplicity, these machines are the basis of almost all mechanical systems. There are 6 classic types of simple machines. The lever, which consists of a rigid bar that pivots on a fulcrum, a seesaw, a lever, or even a bottle opener uses this principle by applying force on one side to lift an object on the other. The pulley changes the direction of force by means of a rope and a wheel, making it easier to lift heavy loads, as seen in cranes and flagpoles. The wheel and axle reduce friction, allowing movement with less effort, and are found in everything from bicycles to doorknobs. The inclined plane is a sloping surface that reduces the effort required to lift objects. It is easier to go up a ramp than lift a heavy object vertically. The wedge converts force into a splitting action, like an axe or knife. The screw is essentially an inclined plane wrapped around a cylinder that transforms rotational force into linear motion, allowing objects to be fastened or materials lifted. Simple machines do not generate energy, but redistribute force over a distance, making tasks more manageable. A longer ramp requires less effort, but you must travel a greater distance. A lever with a well-placed fulcrum amplifies effort, allowing a small force to move a heavy object. Engineers combine simple machines into complex systems. Gears, engines, and construction tools derive from these basic principles. Understanding them provides insight into the mechanics of motion, force, and efficiency, which are the basis of countless innovations throughout history, whether in ancient civilizations or modern technology. Simple machines shape how we interact with the physical world. The mechanical advantage. Lifting a heavy rock with bare hands is almost impossible, but with a lever, the task becomes manageable. This is the mechanical advantage, the principle that allows simple machines to amplify force, making work easier by redistributing effort. The mechanical advantage is a relationship that compares the output force a machine provides with the input force applied. In essence, it tells us how much a machine multiplies our effort. A lever, for example, allows lifting something heavy with a small applied force, increasing the distance over which force is exerted. Different machines achieve mechanical advantage in different ways. Depending on the fulcrum's position, they can multiply the force or increase the speed. A pulley system reduces the effort needed to lift an object by distributing force across several ropes. An inclined plane allows moving heavy objects with less effort by extending the distance the force is applied. In each case, the work remains the same, but the force needed to complete the task decreases. A key concept in mechanical advantage is compensation. While machines reduce the force needed, they increase the distance over which the force is applied. A longer ramp requires less effort to push an object upwards, but the distance traveled increases. A pulley system reduces the effort by half, but requires pulling twice the rope's length. The mechanical advantage constitutes the basis of engineering and mechanics, and influences everything from construction cranes to bicycle gears. By understanding how force is manipulated, engineers design tools, machines, and structures that make modern life possible, whether to lift, cut, or move. The mechanical advantage ensures that great results can be achieved with small efforts. The oscillations, a swing that moves back and forth, a plucked guitar string that vibrates, the pendulum of a clock that marks the passage of time, all these are examples of oscillations, one of the most fun movements in physics. An oscillation is any repetitive movement around a central position. It occurs when an object is displaced from its equilibrium and experiences a restoring force that pushes it back. But instead of stopping at equilibrium, the object overshoots and moves in the opposite direction, repeating the process in a rhythmic cycle. A classic example is a mass on a spring. When stretched and released, the mass oscillates up and down, and the further it moves from its resting position, the stronger the restoring force that pushes it back. This interaction between force and displacement drives the oscillatory movement. Oscillations are classified according to their nature. Mechanical oscillations include systems such as pendulums and vibrating strings. Electromagnetic oscillations, such as alternating currents, involve the displacement of energy between electric and magnetic fields. Quantum oscillations even appear on an atomic scale and govern the behavior of particles. Two key properties define an oscillation: the period and the frequency. Frequency. The period is the time it takes to complete a cycle, while the frequency measures how many cycles occur each second. These values depend on factors such as mass, stiffness, or length. In mechanical systems, oscillations are everywhere, from heartbeats to light and sound waves. They constitute the backbone of countless technologies, from timekeeping devices to radio signals. By understanding oscillatory motion, we gain a deeper insight into nature's repetitive patterns, allowing us to harness its power in engineering, communication, and science. Wave concept. A stone falls into a calm pond, and the waves propagate outwards in perfect circles. A gust of wind tilts a field of tall grass in rhythmic waves. A sound travels through the air and reaches your ears as a melody. All these are examples of waves, one of the most fundamental ways in which energy moves through the universe. A wave is a disturbance that transfers energy through a medium or space without permanently displacing the particles that compose it. Instead of transporting matter, waves transmit energy by causing oscillations. These oscillations can take different forms, giving rise to two main types of waves: mechanical and electromagnetic. Mechanical waves, such as sound, water waves, and seismic activity, need a medium, air, water, or solid ground, to propagate. They move in two ways: longitudinal waves, in which the disturbance moves parallel to the wave's movement, and transverse waves, in which the disturbance moves perpendicularly to the wave's direction. Electromagnetic waves, such as light, radio signals, and X-rays, do not need any medium to propagate, as they can travel through the vacuum of space, making them responsible for everything from the sun's heat to the signals on your phone. Waves are defined by properties such as wavelength, frequency, and amplitude. The wavelength is the distance between two wave peaks. The frequency measures how many cycles occur per second, and the amplitude determines the wave's energy. From the smallest vibrations of atoms to the enormous waves of the ocean, waves govern how energy moves through the world. They're the basis of sound, vision, communication, and even quantum mechanics. Understanding waves allows us to harness their power in everything from music to medical imaging, revealing the profound connections between movement, energy, and information. Simple harmonic motion. A pendulum swings back and forth. A mass moves up and down on a spring. A child on a swing moves rhythmically. All these are examples of simple harmonic motion, SHM, one of the most fundamental types of repetitive motion in physics. SHM occurs when an object oscillates around an equilibrium position under the influence of a restoring force. This force always acts to return the object to its original position and is directly proportional to the distance the object has been displaced. The more it moves, the stronger the force that pushes it back. Think of a spring. When you stretch and release it, the spring pushes the mass towards the center, but due to the impulse, the mass moves beyond, stretching the spring in the opposite direction. This continuous back and forth movement defines SHM. The same principle applies to a pendulum. Gravity acts as a restoring force that pushes it towards the lowest point, only for it to swing and repeat. A key feature of SHM is its periodicity. The movement repeats at regular intervals. The time it takes to complete a cycle is called the period, while the number of cycles per second is frequency. The oscillation speed depends on factors such as the mass and stiffness of the spring or the length of pendulum. SHM is everywhere, from the vibrations of atoms to the movement of planets with small perturbations. It is the basis of countless real-world systems, from clocks to musical instruments. Understanding it allows us to design stable structures, efficient machines, and even predict the behavior of waves and sound, whether microscopic or cosmic. The universe moves to the rhythm of simple harmonic motion. Frequency. A hummingbird flaps its wings so fast that they blur before your eyes. A high-pitched whistle cuts through the air, while a deep drumbeat shakes the ground. These seemingly different phenomena share a common thread: frequency, the speed at which something repeats over time. In physics, frequency is the number of cycles of a repetitive event per unit time. It tells us how fast something oscillates or vibrates, whether sound waves, light waves, or even the ticking of a clock. Frequency is everywhere and is measured in hertz, where 1 hertz equals 1 cycle per second. Let's consider an oscillating pendulum. If it completes a complete back and forth movement every second, its frequency is 1 hertz. If it oscillates faster and completes 5 cycles per second, the frequency increases to 5 hertz. The same principle applies to waves, whether in water, sound, or light. In sound, frequency determines the pitch. A low-frequency wave produces a low and deep note, while a high-frequency wave creates a high-pitched and strident sound. Light behaves similarly. Higher frequencies correspond to blue and violet tones, while lower frequencies appear as red. Beyond everyday experiences, frequency plays an important role in radio signals, quantum mechanics, and even biological rhythms, heartbeats, brain waves, and electromagnetic radiation, which operate at specific frequencies. Understanding frequency allows us to control and manipulate waves in technology, from wireless communication to medical imaging. It defines how energy moves through the universe, shaping the way we perceive and interact with the world. The period is the time it takes for a clock pendulum to swing back and forth. A child on a swing moves with rhythmic motion, and the waves of the sea break on the shore in constant succession. Each of these movements follows a repetitive cycle, and the period is what measures the time it takes to complete a cycle in physics. The period is the time it takes for a repetitive event to complete a full cycle, whether a pendulum swinging, a guitar string vibrating, or a planet orbiting. The period defines the time it takes to return to the starting point and is measured in seconds per cycle. Let's imagine a Ferris wheel. If it takes 30 seconds to make one complete turn, that is its period. If the Ferris wheel accelerates and completes a full turn in 15 seconds, the period decreases. This concept applies to all forms of oscillatory motion, from mechanical vibrations to electromagnetic waves. The period and frequency are closely related. While frequency tells us how many cycles occur in 1 second, the period tells us how long each cycle lasts. They are inversely proportional. A high-frequency wave has a short period, while a low-frequency wave has a long period. In everyday life, the period helps us understand rhythmic movement, heartbeats, sound waves, and even the blinking of traffic lights. It plays a fundamental role in engineering, music, astronomy, and wave mechanics. By understanding the period, we gain a deeper insight into how systems behave over time, whether in the ticking of a clock or in the orbit of celestial bodies. The concept of period allows us to quantify and predict the natural rhythms that govern movement throughout the universe. Wavelength. Imagine you are standing at the edge of a calm lake and throw a stone into the water. The waves propagate outwards in perfect repeating patterns. The distance between 2 consecutive peaks of these waves is what we call wavelength, a fundamental property of waves that determines their behavior in physics. Wavelength is the physical distance between 2 identical points in a wave cycle, whether from crest to crest in a sea wave, from peak to peak in a sound wave, or a complete oscillation in a light wave. It plays a key role in defining how waves interact with the world. In light waves, wavelength determines color. The longer the wavelength, the redder the light. The shorter, the bluer. Radio waves, with wavelengths as long as skyscrapers, carry signals invisibly over great distances. For their part, X-rays, with wavelengths shorter than an atom, penetrate flesh but are blocked by bones, making medical imaging possible. In sound waves, wavelength determines pitch. A low-frequency, long-wavelength wave produces a low, deep sound, while a short-wavelength wave gives rise to a high-pitched tone, like a whistle. Wavelength also determines how waves interact with obstacles. Longer wavelengths curve around barriers, which explains why we can hear sounds coming from behind corners. Short waves, such as visible light, travel in a straight line, and cast sharp shadows. Understanding wavelength is fundamental in fields ranging from communication to quantum physics. They define how we see, hear, and experience the universe, controlling the color of the sky, the melody of a song, or the functioning of a radio. Wavelength is one of the invisible rules that shape reality. The amplitude, a wave breaking in the ocean, the dull sound of a drum, the flickering brightness of a star, all are driven by the amplitude, the measure of how intense or powerful a wave is, whether sound, light, or movement. Amplitude determines the wave's strength. In physics, amplitude is the maximum displacement of a wave from its rest position. It represents the distance a vibrating object moves from its equilibrium. Imagine a child on a swing. If it barely moves, the swing's amplitude is small, but if it swings a lot, the amplitude is large. The greater the amplitude, the more energy a wave carries. In sound waves, amplitude determines volume. A whisper has a small amplitude while thunder has a much larger one. The same applies to light waves. Greater amplitude means greater brightness, while smaller amplitude results in dimmer light. In seismic waves, amplitude defines the intensity of an earthquake. Small tremors produce barely perceptible movements, but large amplitudes can collapse buildings. The amplitude is also crucial in radio signals and electronic waves. A greater amplitude means clearer signals, so adjusting the amplitude in broadcasting changes the strength of transmission, unlike the frequency, which affects the tone or color. Amplitude influences intensity. Two waves with the same frequency can have very different amplitudes, meaning they oscillate at the same rate but carry different amounts of energy. From the waves in a pond to the vibrations of an earthquake, the amplitude is a fundamental property of waves that controls the force behind the movement, the sound, and the light. It is what makes waves not only move but matter. Speed of waves. Imagine watching waves break on the shore. Some roll slowly, while others advance quickly and reach the beach in rapid succession. The speed at which a wave travels is known as wave speed, a fundamental concept determining how energy moves through different media. Wave speed is the rate at which a wave propagates through space or a material. It depends on two key factors: the wavelength, the distance between the crests of the waves, and the frequency with which those crests pass through a certain point. The greater the wavelength or frequency, the faster or slower the wave will be, depending on the medium. Let's consider sound waves in the air, which travel at about 343 meters per second. But in water, they move almost 4 times faster, and in solid materials, such as steel, they can reach speeds of over 5,000 meters per second. This occurs because molecules of solids are more compact, allowing vibrations to be transferred more efficiently. In light waves, the speed of the waves reaches a universal limit, approximately 300,000 kilometers per second, the speed of light in a vacuum. When light enters denser materials like glass or water, it slows down due to interactions with atoms, curving in the process, a phenomenon known as refraction. Sea waves behave differently. Their speed is influenced by depth and gravity. In deep water, longer wavelengths move faster, creating the gentle waves seen far from the coast. As they approach shallower regions, they slow down and increase in height before breaking. Understanding the speed of the waves is essential in fields ranging from seismology to telecommunications, since it determines how earthquakes are detected, how signals travel through fiber optic cables, and even how astronomers study distant galaxies, whether through air, water, or space. Wave speed determines how energy and information move through the universe. The sound waves. The sound surrounds us and shapes the way we experience the world, from a distant thunder to the subtle creak of a floorboard. Every noise we hear is carried by sound waves, vibrations that travel through air, water, or solid matter. But what exactly is a sound wave, and how does it reach our ears? In essence, sound results from the movement of particles in a medium. When an object vibrates, whether a plucked guitar string or the cone of a speaker, it disturbs the air molecules around it, creating alternating regions of compression and rarefaction. These pressure fluctuations propagate outward in all directions, forming a wave that carries energy through the medium. Unlike light, which can travel through empty space, sound needs a medium to exist. In a vacuum of space, there are no air molecules to transmit vibrations, making sound impossible. However, in dense materials like water or metal, sound travels faster because the particles are more compact, allowing energy to be transferred more efficiently. The speed of sound depends on the medium. In dry air at room temperature, it moves at about 343 m per second. In water, almost 5 times faster, and in steel it reaches more than 5,000 meters per second. Sound waves also vary in frequency, that is, in the number of vibrations per second. High frequencies produce high-pitched sounds, such as a whistle, while low frequencies create low and deep tones. This range goes from low bass to high treble. They define how we perceive sound, from music to speech and sonar technology. Sound waves influence almost every aspect of our lives, transporting voices across a room or traveling great distances across the ocean. They are one of the most essential forms of communication in the physical world. Resonance. A small push at just the right moment can set something into powerful movement. This is the essence of resonance, a phenomenon in which an object or system vibrates with increasing amplitude when exposed to periodic forces at its natural frequency. From musical instruments to collapsing bridges, resonance appears across physics, engineering, and everyday life. All objects have a natural frequency, the specific rate at which they vibrate naturally when disturbed. When an external force coincides with this frequency, energy is absorbed efficiently, causing the vibrations to strengthen. A classic example is pushing a swing. If each push is perfectly synchronized with the swing's movement, the oscillations increase drastically with little effort. Resonance plays a crucial role in acoustics. When a guitar string is played, the sound box vibrates in synchrony with the string, amplifying its sound. In wind instruments, air columns resonate at precise frequencies, shaping musical notes. In structural engineering, resonance can be destructive. The Tacoma Narrows Bridge disaster in 1940 is a famous case. Strong winds induced oscillations that coincided with the bridge's natural frequency, causing it to twist violently and collapse. This highlighted the importance of designing structures to withstand unwanted effects of resonance. Beyond mechanics, resonance is vital in electricity. LC electrical circuits, combinations of inductors and capacitors, resonate at specific frequencies, allowing the tuning of radios and the processing of signals. In atomic physics, magnetic resonance is the basis of MRI scanners, in which precise frequencies manipulate atomic nuclei to create detailed images of the human body. Resonance is everywhere, amplifying waves of energy when conditions align perfectly, whether producing sound, driving technology, or shaping natural forces. Resonance demonstrates the immense impact of time and frequency on the physical world. Pressure. Every time you step on the ground, fill a balloon, or submerge yourself underwater, you interact with pressure, the force applied over an area. It is an invisible but fundamental force that shapes everything from the air we breathe to the way fluids move. In essence, pressure is the amount of force exerted per area. Imagine pressing a finger against your palm. Now, push with the same force using a sharp needle. The needle exerts much more pressure because the force is concentrated in a smaller area. That is why knives cut and high heels can leave deep marks on soft surfaces. In fluids, pressure behaves in a unique way. Pascal's principle states that in an enclosed fluid, pressure is transmitted equally in all directions. This is why hydraulic systems work by applying force to a part of a confined liquid. The pressure propagates throughout the liquid, allowing control of enormous forces with minimal effort. It is the same principle that allows car brakes and hydraulic elevators to function efficiently. In gases, pressure is linked to molecular movement. Air molecules are constantly moving, colliding with surfaces and exerting force. When you pump air into a tire, you increase the number of molecules inside, which collide more frequently, increasing pressure. Atmospheric pressure is another key factor. At sea level, the weight of the air above creates a significant force. As you climb a mountain, the air is thinner, meaning there is less pressure, so sealed bags expand at high altitude. Understanding pressure helps explain weather patterns, deep-sea diving, and even how airplanes fly. It governs the way gases, liquids, and solids interact, making it a crucial concept in physics, engineering, and everyday life. Fluid statics. Imagine diving into a pool. As you descend, you feel the pressure around you increasing. This is fluid statics in action, the study of fluids at rest and the forces they exert, whether the pressure at the bottom of the ocean, the buoyancy that keeps ships afloat, or the weight of the atmosphere pressing on us. Fluid statics explains how fluids behave at rest under the action of forces. One of the key principles of fluid statics is the pressure in a fluid inside a container. A fluid exerts pressure in all directions, which increases with depth. That is why the walls of a dam are thicker at the bottom, since they must withstand greater pressure from the water above. The equation of pressure in a fluid shows that pressure depends on depth, density, and gravity, not on the container's shape. A crucial effect of this pressure is buoyancy, discovered by Archimedes. When an object is submerged in a fluid, it experiences an upward force equal to the weight of the fluid it displaces. That is why heavy steel ships float, while a solid steel ball sinks. If the buoyancy force is greater than the object's weight, it rises. If it is less, it sinks. Fluid statics also explains Pascal's principle, which states that a change in pressure in a confined fluid is transmitted equally in all directions. This principle is the foundation of hydraulic systems, which allows small forces to lift enormous objects, from car brakes to construction machinery, through submarines, which balance buoyancy, or air pressure, which affects weather patterns. Fluid statics governs many invisible forces that shape our world. Understanding these principles helps engineers, scientists, and designers harness the power of fluids, whether in the exploration of the sea depths or in everyday hydraulic machines. Fluid dynamics, the water that runs through a river, the air that turns around the wing of an airplane, the blood that flows through the veins, all of this is governed by fluid dynamics, the study of how fluids move. Unlike fluid statics, which deals with fluids at rest, fluid dynamics explains movement, turbulence, and flow patterns shaping everything from weather systems to engineering wonders. One of the key concepts of fluid dynamics is the streamline. Flow versus turbulent flow. In laminar flow, the fluid moves smoothly in parallel layers, like oil flowing through a pipe. In turbulent flow, chaos takes over and eddies and vortices form, like gusts of wind around a building or water breaking against rocks in a river. Whether a fluid flows smoothly or turbulently depends on factors like speed, viscosity, and obstacles in its path. A crucial principle that governs the movement of fluids is Bernoulli's principle, which states that as the speed of a fluid increases, its pressure decreases. This explains how airplanes stay in the air. Air moves faster over the curved top of a wing, creating lower pressure and generating lift. The same principle helps spray bottles work. Moving air reduces pressure and pushes liquid upward. Another key idea is the continuity of flow, which states that the speed of the fluid changes with the size of the pipe. A wide river slows down, while a narrow nozzle accelerates the water, like a thumb partially blocking a garden hose. That is why blood moves faster in narrow arteries than in wider veins. From weather patterns to car aerodynamics, fluid dynamics shapes the world around us. Engineers and scientists use these principles to design everything from efficient water systems to airplanes, harnessing the power of moving fluids to improve technology, transportation, and medicine. Understanding fluid dynamics reveals the invisible forces guiding movement in nature and technology. Viscosity. Imagine pouring honey and water side by side. Water flows effortlessly, but honey moves slowly, forming thick, sluggish jets. This flow difference is due to viscosity, the measure of a fluid's resistance to movement. Viscosity describes how easily fluids flow. Low-viscosity fluids, such as water or air, move freely, while high-viscosity fluids, such as honey or lava, resist movement and flow much slower. This resistance arises from the internal friction between the fluid's molecules. In a high-viscosity fluid, molecules interact strongly, resisting movement. In a low-viscosity fluid, these interactions are weaker, allowing smoother movement. Temperature plays a key role regarding viscosity. When honey is heated, it flows more easily because molecules move faster and interact less. Similarly, cold engine oil thickens, making it difficult for the engine to run smoothly. That is why engine oils are designed to operate over a wide temperature range, ensuring proper lubrication in different conditions. Viscosity also affects how objects move through fluids. In a swimming pool, moving your hand through water is easy, but doing so in a pool of syrup would require much more effort. This resistance is why some animals, like penguins and dolphins, have developed streamlined bodies to reduce drag and move efficiently through water. In practical applications, viscosity is crucial across industries from food production to medicine. It determines how easily paint spreads, how fuel flows in engines, and even how blood circulates within the body. Understanding viscosity helps explain fluid behavior in nature and technology. It governs how liquids and gases move, making it a fundamental concept in physics, engineering, and daily life. Touch a metal railing on a hot day and it will burn. Hold an ice cube and your fingers will go numb. These sensations relate to temperature, a measure of how hot or cold something is. But what is temperature really in essence? Temperature is a measure of the average kinetic energy of particles in a substance. When particles move faster, they have more energy and temperature rises. When they move slower, temperature drops. It is not about the object's size or amount, but about how much movement exists at the microscopic level. Temperature is measured using different scales. The Celsius scale, commonly used worldwide, where water freezes at 0 and boils at 100 degrees Celsius, and the Fahrenheit scale, used mainly in the United States, sets these points at 32 and 212 degrees Fahrenheit. However, scientists rely on the Kelvin scale, in which absolute zero, the lowest possible temperature where molecular motion almost stops, is set at 0 Kelvin. Heat and temperature are closely related, but not the same. Heat is the transfer of energy due to the temperature difference, while temperature itself is just a measure of energy. A bathtub full of hot water contains more total thermal energy than a cup of boiling water, even though the cup is hotter, because the bathtub contains far more water molecules. Temperature governs everything from weather patterns to chemical reactions throughout space. Temperatures plummet to extremes, while nuclear fusion generates heat inside stars. Beyond the imaginable, even on Earth, life depends on temperature balance. Our bodies regulate temperature to function efficiently. Understanding temperature is essential in physics, engineering, and daily life, whether cooking, driving, or even feeling the sun's heat. The temperature is fundamental to how we experience and interact with the world. Heat is energy in motion. It is what makes metal shine in a forge, what makes water boil in a pot, and what makes ice melt in the hand. But heat is not a substance. It is the transfer of thermal energy from one place to another. At the atomic level, everything is in motion. The faster atoms and molecules move, the more energy they have. Heat flows when this energy transfers from a hotter object to a colder one. This occurs in three main ways: conduction, convection, and radiation. Conduction occurs by direct contact. When you touch a hot pan, heat flows from the metal to your skin because the rapidly moving particles collide with the slower ones and transfer energy. Metals conduct heat efficiently because their atoms are very close, allowing energy to move quickly. Convection occurs in fluids, liquids, and gases, where warmer, less dense regions rise, while colder, denser regions sink. This cycle creates currents, such as the movement of air in the atmosphere or the circulation of water in a hot pot. Radiation does not require contact or medium. The sun heats Earth through electromagnetic waves that carry energy through space. That is why you feel the heat of a fire, even if you do not touch it. Unlike temperature, which measures the average energy of particles, heat measures the total energy transfer. A spark from a match may be hot, but it carries far less heat than a cup of hot water because it has fewer particles. Heat plays a crucial role in nature and technology. It drives weather systems, powers engines, and makes life possible on Earth. Understanding heat allows us to harness its power, from cooking food to generating electricity, making it one of the most essential forms of energy transfer in the universe. Zeroth law of thermodynamics. Imagine you're holding a cup of hot coffee. Over time, the heat spreads, warming the cup and slightly cooling the coffee. Eventually, both reach the same temperature. This simple observation leads to one of the most fundamental principles of thermodynamics, the Zeroth law. The Zeroth law of thermodynamics states that if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In other words, if object A is at the same temperature as object C and object B is also at the same temperature as object C, then A and B must be at the same temperature. This may seem obvious, but it is the basis of how we define and measure temperature. Consider a thermometer. When placed in contact with a substance, the liquid or sensor of the thermometer adjusts until it reaches thermal equilibrium with the substance. Thanks to the Zeroth law, we trust that the thermometer reading accurately reflects the temperature of what it measures. This law is fundamental because it establishes temperature as a measurable and significant quantity. Without it, we would not have a coherent way to compare temperatures, which would make thermodynamics and much of modern science impossible. The Zeroth law is seemingly simple, but essential. It ensures that heat flows predictably, allowing us to understand energy transfer, design engines, and regulate climate. It is the reason why you can trust a thermostat, the reason why heat is distributed evenly, and the principle that defines the very concept of temperature. First law of thermodynamics. Energy cannot be created or destroyed. It can only be transferred or transformed. This fundamental principle is the basis of the first law of thermodynamics, a cornerstone of physics that governs everything from the movement of planets to the operation of your car engine. The first law of thermodynamics states that the total energy of an isolated system remains constant. Energy can change form. Heat can convert into mechanical work. Chemical energy can convert into electrical energy, but the total amount of energy always remains the same. This law is essentially an affirmation of energy conservation. Imagine a cup of hot tea. Over time, the thermal energy of the tea transfers to the surrounding air, cooling the liquid. But where does that heat go? It does not disappear. It spreads to the environment, heating the air molecules. Similarly, when you eat food, the chemical energy stored in it converts into kinetic energy when you move, thermal energy when you stay warm, and even electrical signals in your brain. The first law also explains how engines work. When fuel burns in a car engine, chemical energy transforms into heat, which then converts into mechanical work that propels the car forward. Not all energy is converted into useful work. Some is always lost in the form of heat, so no machine is 100% efficient. This principle governs all energy exchanges in the universe, from biological metabolism to industrial power plants. All processes follow the first law, ensuring that although energy constantly changes from one form to another, its total amount remains unchanged. Whether it is the sun heating Earth or a battery powering a phone, energy is never lost. It is only reorganized. Second law of thermodynamics. If left to itself, all energy tends to disorder. Ice melts, batteries die, and stars go out. This is the second law of thermodynamics, one of the most fundamental principles of physics that governs the direction of all natural processes. In essence, the second law states that in any transfer or transformation of energy, the total entropy of a system and its environment will always increase. Entropy is a measure of disorder, randomness, or order. A highly ordered system, such as a stack of perfectly stacked books, has low entropy, but if the books fall to the ground in a scattered mess, entropy increases. The universe naturally moves toward greater entropy. Let's consider heat flow. A cup of hot coffee left in a room will cool, while the surrounding air will warm slightly. Thermal energy spreads and never spontaneously concentrates in the coffee. This unidirectional heat transfer from hot to cold is an irreversible process dictated by the second law. This principle explains why machines are never 100% efficient. Some energy is always lost as heat that dissipates into the environment. Even living organisms must constantly consume energy to counteract entropy and maintain order. On a cosmic scale, the second law predicts the ultimate fate of the universe over immense time scales. All energy will be dispersed. The stars will go out, and the cosmos will reach a state of maximum entropy, often referred to as thermal death. From engines to ecosystems, all systems follow this rule. Energy disperses, structures decompose, and disorder grows. The second law of thermodynamics defines the arrow of time, ensuring that, while energy remains constant, its ability to perform useful work steadily decreases. Third law of thermodynamics. Imagine a world without movement, where atoms and molecules are completely motionless. This is the extreme scenario described by the third law of thermodynamics, which states that, as a system approaches absolute zero, the lowest possible temperature, its entropy or disorder also approaches a minimum value. Absolute zero is the theoretical point at minus 27,315 degrees Celsius, 0 Kelvin, where all molecular motion would cease. According to the third law, as a substance cools, its particles lose energy and stabilize into a more ordered state. At absolute zero, a perfectly crystalline substance, without atomic defects or irregularities, would have zero entropy, since there would be no randomness left in its arrangement. Why is this important? Because it sets a fundamental limit for temperature and energy. No matter how advanced our technology is, we can never reach absolute zero, only approach it asymptotically. The reason is simple. Eliminating that last bit of thermal energy would require infinite effort. The effects of this law can be observed in cryogenics and superconductors. As materials approach absolute zero, their electrical resistance can disappear, completely leading to superconductivity, a state in which electricity flows without energy loss. This is crucial for technologies such as MRI machines and quantum computers. The third law of thermodynamics reinforces the concept that there is always a fundamental limit to the amount of disorder that can be removed from a system. It defines the limit of cold, shapes our understanding of low-temperature physics, and demonstrates that, even in a universe dominated by entropy, there is an unattainable final state of perfect order, the ideal gas. Gases may seem unpredictable as they expand, compress, and flow freely, but beneath this apparent chaos, their behavior follows a simple but powerful rule, the ideal gas law. This fundamental principle describes the relationship between the pressure, volume, and temperature of a gas, showing how they interact under different conditions. In essence, the ideal gas law states that if one property of a gas changes, the others must adjust accordingly. When heating a gas, its particles move faster, increasing pressure. If the volume is fixed, the volume and pressure decrease, since the particles have more space to move. If the gas is cooled, everything slows, reducing both pressure and volume. These relationships explain why a balloon shrinks when it is cold, or why a sealed container can explode if heated. The ideal gas law is an approximation that assumes that gas particles move freely and do not interact. Beyond simple collisions, although real gases deviate under extreme conditions, this law works very well for everyday applications. It governs everything from weather patterns and engine performance to how your lungs work when you breathe. This law also helps scientists understand the behavior of gases in space, where pressure changes can lead to dramatic expansions or compressions. That is why engineers who design spacecraft and deep-sea submersibles rely on the laws of gases to predict how materials will respond to changes in their environment. The ideal gas law is more than just an equation. It is the key to unlocking the hidden order of gases, demonstrating that even the most chaotic systems follow fundamental rules, whether in laboratories, industrial processes, or in the natural world. This law reveals the precise balance between pressure, volume, and temperature, making it an essential tool in physics and engineering. Kinetic theory of gases. Imagine a room full of countless invisible particles moving chaotically, colliding with each other and with the walls at incredible speeds. Although we cannot see it, this microscopic chaos explains how gases behave. This is the kinetic theory of gases, a model that reveals how gas particles move and interact, which forms the basis of our understanding of pressure, temperature, and volume. In essence, the kinetic theory states that gases are made up of tiny particles, atoms, or molecules, in constant random motion. These particles move in straight lines until they collide with each other or with the walls of the container that contains them. These collisions are what create pressure. When gas particles collide with a surface, they exert force. The more frequent and energetic the collisions, the greater the pressure. The temperature is directly related to the movement of gas particles. When a gas is heated, its particles move faster, increasing both pressure and volume if the gas is allowed to expand. Conversely, when cooling the gas, the particles slow, reducing their energy and decreasing pressure. The kinetic theory also explains why gases compress and expand so easily. Since most of the volume of a gas is empty space, the particles can compress together under pressure or separate when pressure decreases. This principle is essential in everything from inflating balloons to understanding how pressure is maintained in the cabins of airplanes at high altitude. This theory is not only an abstract idea, but a tool used in engineering, meteorology, and even space exploration. It helps scientists predict how gases behave under different conditions, allowing innovations in everything from combustion engines to climate modeling. By understanding the constant movement of gas particles, we discover the hidden dynamics that shape the world around us. Phase transitions. An ice block melts to water. The water heats and becomes steam. These transformations may seem simple, but they reveal one of physics' most fundamental principles: phase transition. They describe how matter changes between solid, liquid, and gaseous states, governed by temperature and pressure. At the core of phase transitions is energy. All substances are composed of molecules in constant motion. In a solid state, molecules are very compact and vibrate in place. As heat is added, they gain energy and are released from their rigid structures. This is melting, where solid becomes a liquid. The reverse process, freezing, occurs when energy is removed, slowing molecular motion until they lock in place. Liquids have more freedom. Their molecules slide over each other. But with enough heat, they reach their boiling point, where the molecules gain enough energy to separate completely and form a gas. This is evaporation. The opposite, condensation, occurs when the gas cools and the molecules lose energy, clumping together to form a liquid. Not all transitions occur between common phases. In extreme conditions, matter enters states, such as plasma, in which atoms are stripped of electrons, creating charged particles found in stars and lightning. There is also the mysterious Bose-Einstein condensate, in which atoms near absolute zero behave as a single quantum entity. Phase transitions not only occur when ice melts in your drink, but explain weather patterns, refrigeration, and even help scientists understand the behavior of matter at the smallest scales, from the water cycle to advanced physics. These transformations reveal how energy shapes the physical world. Statics. An imposing bridge, a skyscraper, or even a ladder leaning against a wall. What keeps them standing? The answer lies in statics, the branch of physics that studies forces in equilibrium. When an object is at rest or moving at constant speed, the forces acting on it must be perfectly balanced. At the core of statics is Newton's first law, which states that an object remains at rest unless acted on by an unbalanced force. In static systems, each force is counteracted by another, creating a stable structure. A suspension bridge, for example, stays in place because the force of gravity pulling it down is exactly balanced by the tension of the cables holding it up. Statics is based on two fundamental conditions for equilibrium. Translational equilibrium means that the sum of all forces acting on an object is zero, preventing movement. Rotational equilibrium ensures that the sum of all torques is zero, preventing rotation. Let's imagine a seesaw with equal weight on both ends. It remains level because the forces and torques are balanced. The applications of statics in the real world are everywhere. Architects use statics to design buildings that withstand wind and weight. Engineers apply it to bridges, cranes, and towers to ensure stability. Even something as simple as stacking books requires understanding the balance and distribution of forces. Understanding statics allows us to predict how structures will behave under different conditions. Whether designing a skyscraper or simply setting up a ladder, the principles of statics ensure that objects remain solid, safe, stable, and immobile in a world shaped by forces. Statics is what keeps everything in place. Statistical mechanics. At any moment, the air around you is full of countless molecules moving in random directions, colliding and exchanging energy. It is impossible to follow each individually, but their collective behavior follows predictable patterns. This is the basis of statistical mechanics, a branch of physics that connects microscopic motion with large-scale properties such as temperature, pressure, and entropy. Unlike classical mechanics, which describes the motion of individual objects, statistical mechanics deals with systems containing a large number of particles. It uses probability to determine how these particles behave on average, revealing patterns that emerge from apparent chaos. For example, the temperature of a gas is not a property of a single molecule, but a measure of the average kinetic energy of all molecules combined. One of the key ideas of statistical mechanics is entropy, a measure of disorder in a system. When energy is dispersed, such as heat dissipating from a hot object to a cooler one, entropy increases. This statistical tendency towards greater entropy explains why natural processes, such as the melting of ice or the diffusion of gases, move in one direction rather than spontaneously reversing. Statistical mechanics also provides the basis for understanding phase transitions. For example, when water turns to steam, it is not just a change of state, but a collective change in molecular behavior governed by probability. The same principles apply to solids that melt, magnets that lose their alignment, or even superconductors that operate at low temperatures. This approach extends to quantum mechanics, which predicts the distribution of electrons in atoms and the behavior of complex materials by focusing on averages and probabilities. Statistical mechanics transforms microscopic randomness into macroscopic predictability, forming the backbone of modern thermodynamics and materials science. Every time you flip a switch, charge your phone, or feel a small shock when you touch a doorknob, you are experiencing one of the universe's most fundamental properties, electrical charge. Electric charge is an intrinsic property of matter, responsible for all electrical and magnetic interactions. There exist two types of charge, positive and negative. Opposite charges attract each other, while like charges repel. This simple rule governs everything from how atoms bond to the forces behind lightning on the smallest scale. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. The balance of these charges determines how objects will interact. When electrons move or transfer between objects, they create electrical forces. That's why, when you rub a balloon against your hair, it sticks to the wall. The balloon steals electrons and acquires a negative charge, while the hair is left with a positive charge. Opposites attract, so the balloon adheres. The electric charge is measured in coulombs, in honor of physicist Charles Augustin de Coulomb, who quantified how charges interact. His work laid the foundation for understanding electrostatic forces, demonstrating that the force between two charged objects depends on the magnitude of their charge and the distance between them. But charge not only creates static electricity, but also drives electric currents in metals. Free electrons move through a conductor, creating electricity that powers everything from light bulbs to supercomputers. This movement of charge underpins modern technology, communication, and even life itself. Our nervous system depends on charged ions to transmit signals through the body. Electric charge is not just a property of particles. It is the force that shapes the world, from the smallest electron to the largest electrical storms. Mastering this concept allows us to understand more deeply electricity, magnetism, and the invisible forces that drive our universe. Coulomb's law. Every interaction between charged objects follows a fundamental rule, an invisible force that attracts or separates them. This is Coulomb's law, the principle that governs electrical forces at minuscule scales and over great distances, proposed by Charles Augustin de Coulomb in the 18th century. This law describes how the force between two charged objects depends on two factors: their charge and their separation. The greater the charge, the stronger the force. But as the objects move farther away, the force weakens rapidly. If the distance doubles, the force weakens 4 times as much. This is an inverse quadratic relationship. The same principle governs gravity. To visualize Coulomb's law, imagine two magnets. If you bring them closer, the attraction or repulsion is strong, but if you separate them, the effect weakens. The same happens with electric charges. A particle with a positive charge attracts one with a negative charge, while two like charges repel each other, following the same predictable rule. This law is the basis of electrostatics and applies everywhere. It explains why electrons remain bound to atomic nuclei, how charged particles move in electric fields, and why static electricity makes your hair stand on end when you rub a balloon. Coulomb's law also plays a crucial role in technology, from the design of capacitors and circuits to the interactions between ions in chemistry. Understanding this force is essential even in deep space. The behavior of charged particles in plasma follows Coulomb's principles. Coulomb's law provides an accurate and measurable way to predict and control electrostatic interactions, which forms the basis of many applications in physics and engineering. The electric field cannot be seen, but it is everywhere. It is a force that extends through space and affects everything that has electric charge. This is the electric field, an invisible structure that determines how charged objects interact, even when they do not touch. Any object with charge creates an electric field that extends outward and influences other nearby charges, just as gravity attracts objects without direct contact. If you place a positive charge in an electric field, it feels a force that pushes or attracts it, depending on the direction of the field. The intensity of this force depends on the charge that creates the field and the distance at which it is located. To visualize it, imagine a charged object as a lit candle in a dark room. The light propagates in all directions, just as an electric field extends outward. The closer you are, the stronger the effect. As you move away, the influence fades. Electric fields follow predictable patterns. A positive charge produces a field that radiates outward, while a negative charge attracts field lines inward. When there are multiple charges, their fields interact, forming complex patterns that dictate the movement of nearby particles. This invisible force is fundamental to countless phenomena. Lightning forms due to the intense electric fields between clouds and the ground. The screens of your phone respond to touch using electric fields to detect changes in charge. Even the nerve signals in your body depend on small electric fields to transmit information. The electric field is not just a theoretical concept. It is an essential force that shapes the world at all levels. Understanding it allows us to manipulate electricity, build technology, and explore the hidden forces that govern our universe. Electric potential. The electric potential is the hidden energy behind every spark, each circuit, each moving charge. It is the force that drives electricity, shaping how charges interact and move. In essence, electric potential is the energy amount per unit of charge at a given point in an electric field. It tells us how much work is needed to move a charge from one place to another. Just as a ball at the top of a hill has gravitational potential energy, a charge in an electric field has electric potential energy. The higher the potential, the more energy is available for the charges to move. To visualize it, imagine a waterfall. Water flows from higher to lower height, driven by gravity. Similarly, electric charges move from high to low potential, driven by the electric field. The greater the height difference, the stronger the water flow, just as a greater electric potential difference creates a stronger push for charge movement. This electric potential difference is what we call the voltage. It is what powers all electrical devices, from your phone to huge electrical networks. When you plug in a device, you connect it to a voltage source, creating a path for electric charge to move. Electric potential is more than just a concept. It is the driving force of electricity itself. It determines how charges behave, how energy is transferred, and how we harness electricity to power the modern world, whether in batteries, circuits, or nature. Understanding electric potential is key to understanding how electricity flows. Capacitance is the ability to store electrical charge, a concept that powers everything from camera flashes to computer memory. In its simplest form, capacitance measures the amount of charge a system can store for a given voltage. This is achieved using a capacitor, an electrical component designed to store and then release energy. Capacitance consists of two conductive plates separated by a dielectric insulating material. When connected to a voltage source, electrons accumulate on one plate, while the other becomes positively charged. This separation of charges creates an electric field that allows the capacitor to store energy. To visualize it, imagine a water tank with a flexible membrane at the center. As water is pumped, one side fills, while the other empties, storing potential energy in the stretched membrane. Similarly, a capacitor stores electrical energy until it is needed. The capacitance of a capacitor depends on three factors: the surface area of the plates, the distance between them, and the dielectric material properties. Larger plates store more charge. Closer plates create a stronger electric field, and a better dielectric improves storage capacity. Capacitors have countless applications. They smooth voltage fluctuations in power supplies, help filter signals in audio and radio circuits, and provide the rapid bursts needed in camera flashes and electric vehicles. Unlike batteries, capacitors charge and discharge almost instantly, making them ideal for rapid energy storage. Understanding capacitance is key to mastering electrical circuits, whether to control the flow of energy in simple electronic devices or improve performance in advanced technology. Capacitors are essential to shaping how we store and manage electrical energy. Ohm's law. Electric current is the invisible force that powers the modern world, from the smallest circuits in your phone to the huge electrical networks. Everything works thanks to the movement of electrical charge at its core. Electric current is the flow of charged particles, usually electrons, through a conductor. It is similar to water flowing through a pipe. Just as water moves from high to low pressure, electric charges move from high to low potential when voltage is applied. The amount of current depends on how easily charges can move through the material. This brings us to Ohm's law, the fundamental relationship between voltage, current, and resistance. It tells us that the current in a circuit is directly proportional to the voltage applied and inversely proportional to the resistance. Simply put, if we increase the voltage, more current flows. If we increase the resistance, the current decreases. To understand it, imagine pushing water through a hose. Higher water pressure, voltage, pushes more water current, but if the hose is narrow, high resistance, less water flows. The same principle applies to electricity. A higher voltage pushes more current, while a higher resistance limits it. All electrical devices are based on this principle. Resistors control the flow of current, circuit breakers prevent overloads, and conductors ensure smooth energy transmission. Understanding electric current and Ohm's law is essential for everything from designing electronic devices to managing energy distribution. It is the basis of how electricity moves, how we control it, and how we harness it efficiently, whether in simple circuits or complex electrical systems. These principles define how energy flows in our world. Basic circuit analysis. All electronic devices, from a flashlight to a supercomputer, depend on circuits to function. Understanding how circuits work is fundamental to understanding electricity itself. Circuit analysis is the method used to determine how voltage, current, and resistance interact within a circuit. In essence, a circuit is a closed loop through which electric current flows. If the loop is broken, the current stops, just as a water pipe with a missing section cannot supply water. A basic circuit consists of three key components: a voltage source, such as a battery, which provides the necessary impetus for electrons to move; resistors, which limit the flow of current similarly to narrowing a water pipe; and conductors, the wires that carry electricity between components, much like roads that guide traffic. The analysis of circuits is based on two fundamental laws. Ohm's law relates voltage, current, and resistance, and tells us how much current will flow through a component as a function of the applied voltage and its resistance. Kirchhoff's laws help analyze circuits with multiple loops and branches. Kirchhoff's voltage law states that the sum of the voltages around any closed loop must equal zero, which guarantees the conservation of energy. Kirchhoff's current law states that the total current entering a junction must equal the total current leaving, like cars merging on a highway lanes. By applying these laws, we can calculate how current and voltage are distributed in complex circuits, ensuring their correct operation and safety. This analysis is crucial in the design of everything from domestic wiring to microprocessors. Circuits are the foundation of modern technology. Understanding their behavior allows us to harness electricity efficiently and ensure devices work as intended. AC and DC electricity. Electricity powers everything around us, but not all electricity flows in the same way. There are two main types: alternating current, AC, and direct current, DC. Understanding their differences is key to understanding how electricity works in everything from power grids to smartphones. Direct current, DC, is simple. It flows in a constant direction. Imagine a river flowing smoothly downstream. Electrons travel in a straight line from the power source to the device. Batteries, fuel cells, and solar panels all produce DC electricity. Your phone, laptop, and most small electronic devices run on DC power because it provides stable voltage. Alternating current, AC, on the other hand, constantly changes direction. Instead of flowing in a straight line like a river, it moves back and forth like sea waves. This rapid change occurs many times per second, typically 50 or 60 times per second, hertz, depending on the region. Alternating current is what reaches homes, businesses, and power grids, as it can travel long distances with minimal energy loss. The reason alternating current dominates large-scale electricity distribution is its efficiency. When electricity is transmitted through power lines, high voltage is needed to reduce energy loss. The voltage of alternating current can be easily increased or decreased by transformers, making it ideal for long-distance transmission. However, direct current is more difficult to convert and loses energy more quickly with distance, but DC is not obsolete. Modern advances, such as high-voltage DC transmission and renewable energy systems, depend on it. Most electronic devices use DC, so power adapters and chargers convert AC from outlets to DC. Both AC and DC electricity power the world in different ways. AC dominates large-scale power distribution, while DC keeps our personal devices running smoothly. Each has its own role in how electricity moves through modern technology. Magnetic field. A magnetic field is an invisible force that influences objects without direct contact. It surrounds magnets, electric currents, and even planets, and determines the behavior of charged particles and materials. At its core, a magnetic field is a region of space where magnetic force is exerted. It is produced by the movement of electrical charges and is most commonly observed in magnets and electric currents. The field itself is represented by magnetic field lines that show the direction in which a magnetic force would push a north pole if placed within the field. These lines always emerge from the north pole of a magnet and return to the south pole, forming closed and continuous paths. To visualize a magnetic field, imagine scattering iron filings around a bar magnet. The filings align along the field lines, revealing the otherwise invisible structure of the magnetic field. One of the most significant examples of a magnetic field is the Earth's own magnetic field, generated by the molten iron moving in the planet's core. It protects us from harmful solar radiation and guides compasses, which aids navigation. Similarly, the Sun and other celestial bodies have magnetic fields that influence space, weather, and planetary environments. Magnetic fields also play a crucial role in electromagnetism. When an electric current flows through a wire, it generates a circular magnetic field around it. This principle is used in electromagnets, where coils of wire wrapped around an iron core create a powerful, controllable magnetic field when current passes through. Magnetic fields are essential for countless technologies, from electric motors and transformers to MRI machines and maglev trains. Understanding them allows us to harness their power to shape everything from modern electronics to large-scale planetary interactions. Electromagnetic induction. Imagine converting mechanical motion into electricity. This is the power of electromagnetic induction. It is the principle underlying generators, transformers, and countless modern technologies that keep the world running. In essence, electromagnetic induction occurs when a changing magnetic field generates an electric current in a conductor. This phenomenon was discovered by Michael Faraday in 1831, when he observed that moving a magnet through a coil of wire produced a current. The key is change. If the magnetic field remains constant, nothing happens, but the moment it fluctuates, an electric current is induced. To visualize it, imagine pushing a loop of wire through a magnetic field. As the wire passes through the field lines, the electrons within the wire experience a force that causes them to move. This movement is what we call an electric current. This principle is governed by Faraday's law of induction, which states that the induced voltage depends on the speed at which the magnetic field changes and the number of loops that the conductor has. The faster the change, the stronger the induced current. One of the most important applications of electromagnetic induction is electric generators inside power plants, where turbines spin wire coils within strong magnetic fields, continuously generating electricity. The opposite process, which uses electricity to create movement, is how electric motors work. Another key application is transformers, which use induction to either increase or decrease voltage for efficient energy transmission. Without them, electricity distribution over long distances would be nearly impossible. Electromagnetic induction is the basis for the generation and transmission of electrical energy and shapes everything from how we light our homes to how we charge devices. It is a principle that converts movement into electricity, unlocking electromagnetism's full potential. Faraday's law. What would happen if you could generate electricity by simply moving a magnet? This is the essence of Faraday's law, a fundamental principle explaining how changing magnetic fields create electric currents. This discovery transformed science and technology, paving the way for electric generators, transformers, and even modern electrical grids. Faraday's law states that a changing magnetic field induces an electric current within a conductor. In simpler terms, if a loop of wire is placed near a moving magnet, the movement of the magnetic field causes the electrons in the wire to move, creating a current. The faster the field changes, the stronger the induced current becomes. To understand it, picture a loop of wire near a bar magnet. If the magnet remains stationary, nothing happens, but the moment the magnet moves, the magnetic field around it changes, and an electric current flows through the wire. This phenomenon underlies electromagnetic induction. Faraday's law also tells us that the induced voltage depends on the rate at which the magnetic field changes and the number of loops that the conductor has. The more loops, the more electrons in motion, resulting in a stronger current. This principle powers electric generators, in which wire coils rotate within magnetic fields, producing electricity. It also enables the operation of transformers, which adjust voltage levels for efficient energy transmission. Without Faraday's law, modern electrical systems would not even exist. Every time you charge your phone, use an electric motor, or depend on the electrical grid, you are benefiting from this principle. Faraday's intuition revealed a direct relationship between magnetism and electricity, which continues to power our world today. Lenz's law. What would happen if every action in electricity triggered an automatic resistance, a force opposing the change? This is the essence of Lenz's law, a fundamental rule of electromagnetism governing the behavior of induced currents. Lenz's law states that when a changing magnetic field induces a current in a conductor, the current flows in a direction that opposes the change that created it. In other words, nature resists change. It does not let energy flow freely without pushing back. To see this in action, imagine dropping a strong magnet through a copper tube. Instead of falling freely, the magnet slows down as if it were moving through some invisible liquid. This occurs because the moving magnet induces circular electric currents, called eddy currents, inside the tube. These currents generate their own magnetic field that pushes against the magnet's movement, slowing it down. This opposition is not a coincidence. It is a direct consequence of energy conservation. If the induced current did not resist the change in the magnetic field, energy could appear from nowhere, violating the fundamental laws of physics. Lenz's law plays a crucial role in real-world applications. Electric brakes on roller coasters use it to brake cars without friction. Induction cooktops rely on it to efficiently generate heat, and even transformers and electrogenerators depend on Lenz's law to regulate energy transfer. Understanding Lenz's law reveals how electromagnetism maintains balance. It ensures that each induced current follows a predictable pattern, resisting sudden changes and stabilizing electrical systems, from industrial machines to everyday appliances. This principle quietly governs how electricity flows, ensuring that every push meets an equal and opposite resistance. Maxwell's equations. Electromagnetism governs almost all modern technology, from wireless communications to electrical energy. At its base are the Maxwell equations, a set of 4 fundamental laws that describe how electric and magnetic fields interact. These equations are the backbone of classical electromagnetism, unifying electricity, magnetism, and light into a single framework. The first equation, Gauss's law, states that electric charges create an electric field. Imagine placing a charged balloon out in space. This equation tells us how the electric field radiates outward, just as gravity extends outward from a planet. The second, Gauss's law for magnetism, reveals that magnetic fields always form loops. Unlike electric charges, magnetic poles never exist on their own. Cut a magnet in half, and you will not get separate north and south poles. Each half will still have both. Faraday's law of induction is the third equation and explains how changing magnetic fields generate electric fields. This is the principle underlying electric generators, where rotating magnets induce current in wire coils, converting motion into electricity. The final equation, Ampere's law with Maxwell's correction, shows that electric currents create magnetic fields, and that changing electric fields also generate magnetic fields. This interaction allows electromagnetic waves, like light and radio signals, to propagate together through space. Maxwell's equations not only explain everyday electrical phenomena, but also predict the existence of electromagnetic waves, linking light to electromagnetism. They transformed physics, paving the way for everything from radio to quantum mechanics. Understanding these 4 equations provides a window into the forces that shape our technological world, making them some of science's most profound insights. Electromagnetic waves, light, radio signals, and even the sun's heat. All of them are transported by electromagnetic waves. Unlike sound, which needs air to travel, electromagnetic waves move through the vacuum of space, carrying energy across vast distances. These waves are not just one thing. They result from electric and magnetic fields working together in perfect harmony. An electromagnetic wave is created when an electrical charge accelerates, disturbing the surrounding electric and magnetic fields. These disturbances propagate outward in the form of waves, with the electric and magnetic components oscillating perpendicularly to each other and also to the direction of the wave's movement. This unique property allows electromagnetic waves to travel without a medium, unlike mechanical waves, which need air, water, or solid matter to propagate. The speed of electromagnetic waves in a vacuum is constant, approximately 186,000 miles per second, the speed of light. What differentiates one type of electromagnetic wave from another is its wavelength and frequency. Long wavelength waves, such as radio waves, are used for communication, while shorter wavelength waves, such as X-rays, penetrate materials for medical imaging. In between, visible light represents only a small fraction of the electromagnetic spectrum, allowing us to perceive the world through color. Electromagnetic waves are fundamental to modern technology, making everything possible from wireless internet to GPS navigation and medical imaging. The discovery of these waves confirmed that light itself is an electromagnetic phenomenon, linking optics with electromagnetism. Understanding how they behave allows us to harness their properties to shape everything from everyday communication to the most advanced physics. Whether visible or invisible, these waves form the invisible backbone of the modern world, carrying information, energy, and even glimpses of the cosmos. Electromagnetic waves, light, radio signals, and even the sun's heat are transported by electromagnetic waves. Unlike sound, which needs air to travel, electromagnetic waves move through the vacuum of space, carrying energy across vast distances. These waves are not just one thing. They result from electric and magnetic fields working together in perfect harmony. An electromagnetic wave is created when an electrical charge accelerates, disturbing the surrounding electric and magnetic fields. These disturbances travel outward as waves, with the electric and magnetic components oscillating perpendicularly to each other and to the direction of the wave's movement. This unique property allows electromagnetic waves to travel without a medium, unlike mechanical waves, which need air, water, or solid matter to propagate. The speed of electromagnetic waves in a vacuum is constant, approximately 186,000 miles per second, the speed of light. What differentiates one type of electromagnetic wave from another is its wavelength and frequency. Long wavelength waves, such as radio waves, are used for communication, while shorter wavelength waves, such as X-rays, penetrate materials for medical imaging. In between, visible light represents only a small fraction of the electromagnetic spectrum, allowing us to perceive the world through color. Electromagnetic waves are fundamental to modern technology, making everything possible from wireless internet to GPS navigation and medical imaging. The discovery of these waves confirms that light itself is an electromagnetic phenomenon, linking optics with electromagnetism. Understanding how they behave allows us to harness their properties to shape everything from everyday communication to cutting-edge physics. Whether visible or invisible, these waves form the invisible backbone of the modern world, carrying information, energy, and even glimpses of the cosmos. Light as a wave. Light is more than simple illumination. It is a wave that moves through space with precision and speed, but unlike sound waves or water waves, light does not need a medium to travel. It moves through empty space, carrying energy across vast cosmic distances in an instant. At its core, light is an electromagnetic wave, which means that it consists of oscillating electric and magnetic fields that generate each other as they advance. These fields vibrate perpendicularly to each other, forming a self-sustaining wave that propagates through space at an incredible speed, about 300,000 kilometers per second in a vacuum. This wave nature of light explains many of its behaviors. When light passes through a narrow opening, it scatters, which is known as diffraction. When it interacts with the surface of an oil film or a soap bubble, it creates bright colors, an effect caused by interference. These phenomena would not be possible if light were simply a flow of particles. The wavelength of light determines its color. Longer wavelengths create red light, while shorter ones shift towards blue and violet, beyond what our eyes can see. Infrared light has even longer wavelengths, while ultraviolet rays, X-rays, and gamma rays have much shorter lengths. Together, they form the electromagnetic spectrum, a wide range of energy-carrying waves that shape everything from radio signals to medical images. The wave properties of light not only describe how we see the world, but also drive modern technologies. optical fiber, laser precision, and even the colors of the rainbow. All of this is derived from the wave behavior of light. Understanding light as a wave reveals the hidden structure of reality and shows us that even something as familiar as brightness is a dance of electrical and magnetic forces moving through space. Reflection. Look at yourself in a mirror, and you will see your reflection, but what you are really seeing is light bouncing, moving, and obeying the rules of physics with perfect precision. This is reflection, one of the most fundamental behaviors of light in its essence. Reflection occurs when light strikes a surface and bounces back. This happens because light travels in a straight line, but changes direction when it encounters a boundary. The way it is reflected depends on the surface on which it falls. A smooth surface, such as a mirror, produces a specular reflection, in which light rays bounce in a single organized direction, creating a sharp image. That is why you can see your reflection in a calm lake, but not in a rough ocean. When light falls on a rough surface, it scatters in many directions, producing diffuse reflection. That is why most objects do not act as mirrors, but reflect enough light so that we can see them. The law of reflection governs this process. The angle at which light falls on a surface, called the angle of incidence, is equal to the angle at which it bounces, the angle of reflection. This predictable behavior allows us to design optical instruments, from telescopes to laser systems. But reflection goes beyond mirrors. It is the reason we see the moon, why periscopes allow us to see around corners, and why polished metals shine. Even colors depend on reflection. A red apple looks red because it reflects red wavelengths while absorbing others. Understanding reflection is not just about seeing your own image, but about recognizing how light interacts with the world, revealing details that shape perception and define how we experience everything around us. Refraction. Immerse a straw in a glass of water, and something strange happens. It looks bent, almost broken, but the straw is not changing shape. What you're seeing is light that curves as it passes between air and water. This is refraction. Refraction occurs when light passes from one medium to another, changing speed and direction. Light travels faster in a vacuum, a little slower in air, and even slower in water or glass. When it moves between these materials, it curves because its speed changes. This curvature effect is what makes objects underwater appear distorted or displaced. The amount light bends depends on the refractive index of a material, a measure of how much a substance slows down light. Air has a low refractive index, while water and glass have higher indices. The greater the difference in refractive index, the more light deviates. One of the most striking effects of refraction is the illusion of depth in water. A pool always looks shallower than it really is because light bends as it exits the water, making objects appear closer to the surface than they are. Refraction also plays a fundamental role in optics. The lenses in glasses, microscopes, and telescopes rely on refraction to focus light and correct vision. That is why rainbows are formed. Sunlight curves and scatters inside raindrops, dividing into a spectrum of colors. Without refraction, magnifying glasses would not work, glasses could not correct vision, and the world would not shine through heat waves. It is an invisible force that shapes how we see everything, curving light and perception itself. Diffraction. Have you ever noticed how sound curves around corners, allowing you to hear someone speak even when they are out of your sight, or how light scatters when it passes through a small gap? This phenomenon is called diffraction, the way waves curve, propagate, and interfere when they encounter obstacles. Diffraction occurs with all types of waves, including light, sound, and water waves. It occurs when a wave encounters an edge, a slit, or an obstacle and curves around it instead of traveling in a straight line. The smaller the gap compared to the wavelength, the more pronounced the diffraction. You can see diffraction in everyday life. Have you ever noticed the bright colors on a CD or the rainbow-like glow of a soap bubble? These patterns occur because light waves diffract in the microscopic grooves and interfere with each other to produce vivid colors. Sound waves, which have much longer wavelengths than light, diffract around doors and walls. That is why you can hear someone talking in another room, even if you cannot see them. Radio waves, which are even longer, can curve around buildings and mountains, ensuring that signals reach areas that would otherwise be blocked. Diffraction plays a crucial role in optics and technology. Scientists use diffraction patterns to study the atomic structures of materials, while diffraction gratings are used in spectrometers to analyze light from distant stars. Even in everyday life, the ability of waves to curve and propagate influences everything from photography to audio design. Although often invisible to the eye, diffraction shapes how waves interact with the world, curving around barriers, creating interference patterns, and revealing the hidden nature of waves in motion. Interference. What happens when two waves meet? Do they collide and cancel each other out, or combine to form something new? This is the phenomenon of interference, the way waves interact when they overlap, creating patterns of amplification and cancellation. Interference occurs when two or more waves pass through the same point in space at the same time. When their crests and troughs align, they combine to form a wave with greater intensity. This is called constructive interference. This effect can be observed in the bright bands of light in a soap bubble or in the rumbling sound of two perfectly aligned speakers. But what happens if the crest of one wave meets the trough of another? They cancel each other out, reducing the intensity of the waves. This phenomenon is known as destructive interference. Noise-canceling headphones use this principle by detecting external sounds and generating sound waves that interfere destructively, effectively silencing unwanted noises. A striking example of interference is the double-slit experiment. When light passes through two narrow slits, it does not just produce two bright spots on a screen, but forms a pattern of alternating bright and dark bands. The bright areas occur where the waves reinforce each other, while the dark areas mark the points of cancellation. This experiment revolutionized physics by demonstrating that light behaves like a wave. Interference is not limited to light and sound, but governs the behavior of water waves, radio signals, and even quantum particles, from the bright colors of an oil film to echoes in a concert hall. Interference is a fundamental property of waves that reveals the hidden complexity of their interactions. Field concepts. A force can act on an object even when nothing seems to touch it. This is the essence of field concepts, a fundamental idea in physics that explains how forces extend through space rather than requiring direct contact. Fields allow objects to influence each other at a distance. A field is a region of space where a force is exerted on objects with appropriate properties. For example, a gravitational field surrounds any mass and attracts other masses toward it. The Earth's gravitational field keeps the moon in orbit and causes objects to fall to the ground. Similarly, there is an electric field around charged particles that attracts or repels other charges depending on their type. A magnetic field influences moving charges and magnetic materials, guiding the movement of compass needles or electric currents. Fields are visualized by field lines that trace how a force behaves in space. In a gravitational field, these lines always point toward the mass that creates the field. In an electric field, positive charges push the lines outward, while negative charges pull them inward. The density of these lines indicates the intensity of the field. Closer lines mean stronger forces. Unlike physical objects, fields can exist in empty space. The sun's gravitational field extends billions of kilometers and keeps the planets in their orbits without any direct contact. In electromagnetism, fields play a crucial role in the transmission of forces through space, enabling everything from wireless communication to the operation of electric motors. Fields provide a unified way of understanding forces at a distance. They explain the interactions that shape the universe, from planetary motion to subatomic forces, defining how forces extend through space. Field concepts form the basis of classical physics and modern scientific theories. Black body radiation. Everything around you, from the sun to the screen you're looking at, emits energy in the form of radiation. But how do objects emit and absorb this energy? The answer lies in black body radiation, a fundamental concept in physics that explains how objects shine, radiate heat, and interact with electromagnetic waves. A black body is an idealized object that absorbs all incoming radiation without reflecting or transmitting anything, since it does not reflect light. At low temperatures, it appears perfectly black, but as it heats up, it emits radiation in a spectrum of wavelengths. Imagine a piece of metal heating up in a forge. At first it is dark, then it turns red, orange, and finally white as its temperature increases. This glow is black body radiation in action. In the late 19th century, physicists struggled to explain the precise way in which black bodies emitted energy. Classical theories predicted that, as the wavelength decreased, the emitted energy would approach infinity, a contradiction known as the ultraviolet catastrophe. The decisive breakthrough was made by Max Planck, who proposed that energy is not emitted continuously, but in discrete packets called quanta. This idea gave rise to Planck's law, which accurately describes black body radiation and marks the birth of quantum mechanics. Black body radiation is everywhere. The cosmic microwave background, the glow of the Big Bang, is the black body footprint of the universe. Infrared cameras detect thermal radiation based on these principles. Even the colors of stars are dictated by black body radiation, with hotter stars appearing blue and cooler stars red. Understanding black body radiation was a turning point in physics, bridging classical and quantum theories. It explains why everything that has temperature radiates energy and provides the basis for modern quantum mechanics, astrophysics, and thermal imaging technology. Atomic structure. Everything around you, every solid object, every puff of air, every drop of water is made up of atoms, the fundamental building blocks of matter. Although incredibly small, atoms form the structure of everything in the universe, from the smallest grain of sand to the most massive stars. At the center of the atom is the nucleus, a dense core containing protons and neutrons. Protons have a positive charge, while neutrons have no charge at all. Surrounding the nucleus is a cloud of electrons, negatively charged particles that move in specific energy levels or orbitals. The balance between positively charged protons and negatively charged electrons holds the atom together through electromagnetic forces. Not all atoms are the same. The number of protons in an atom's nucleus, known as the atomic number, determines what element it is. Hydrogen has a single proton, while carbon has 6 and uranium has 92. But the atoms of the same element can vary, since they can have different numbers of neutrons, forming isotopes that can alter the stability and properties of an element. The behavior of atoms is dictated by their electrons. The electrons do not move randomly, but exist at defined energy levels. The way in which these electrons interact and bind with others determines the chemical reactions and the forces that give shape to everything, from the air we breathe to the food we eat. Our understanding of the atomic structure has evolved from the solid spheres of Dalton to the planetary model of B, and, finally, to quantum mechanics, where electrons behave as both particles and as waves. This discovery revolutionized fields like chemistry, electronics, and nuclear energy. Atoms are small, but they contain the secrets of the structure, behavior, and interactions of all matter, a microscopic world that governs everything we observe. Photon concept. Light seems continuous, like a smooth beam flowing through space, but at its most fundamental level, light is composed of discrete packets of energy, photons. The photon is the smallest unit of light, an indivisible quantum of electromagnetic radiation. Unlike particles of matter, photons have no mass, but they carry energy and momentum, making them one of the most fascinating components in the universe. The concept of photons arose from a fundamental problem in physics. Classical wave theories of light could not explain certain behaviors, such as the photoelectric effect, where light ejects electrons from a metallic surface. Albert Einstein proposed a revolutionary solution. Light is not only a wave, but it also behaves like a particle. He suggested that light is composed of quantized packets of energy called photons, and that the energy of each photon is directly proportional to its frequency. This idea revolutionized physics and laid the foundation for quantum mechanics. Photons exhibit properties of both waves and particles, a concept known as wave-particle duality. They travel as waves, interfering and diffracting like waves in water, but interact with matter as discrete particles, transferring energy in precise amounts. This duality allows photons to power everything from solar panels to lasers. Unlike ordinary particles, photons always move at the speed of light in a vacuum, have no rest mass, and do not experience time. They enable vision, communication, and even fundamental interactions within particle physics. From the light of distant stars to the signals in optical fiber, photons shape how we perceive and interact with the universe. Understanding them is not only explaining light, it is unveiling the very nature of reality. Photoelectric effect. Light is not only a wave, it also behaves like a particle. This revolutionary idea was confirmed by the photoelectric effect, a phenomenon that transformed our understanding of physics and helped lay the foundations for quantum mechanics. The photoelectric effect occurs when light strikes a metal surface, ejecting electrons. At first glance, this might seem simple. If light is a wave, increasing its intensity should provide more energy to the electrons, causing them to eject at a higher speed. However, experiments showed something strange. Increasing the intensity of the light did not always work. Instead, electrons were only ejected if the light had a sufficiently high frequency, regardless of intensity. This contradiction puzzled scientists until Albert Einstein proposed a radical solution in 1905. He suggested that light is not only a wave, but also composed of particles called photons, each carrying a discrete packet of energy. The energy of a photon is determined by its frequency, not its intensity. If a photon has enough energy, it can release an electron from a metal. If it does not, electrons are not ejected, regardless of how many photons strike the surface. Einstein's explanation was revolutionary, as it demonstrated that energy is quantized and that light has particle-like properties, reinforcing the idea of wave-particle duality in quantum mechanics. This discovery not only earned Einstein the Nobel Prize in Physics, but also led to the development of photoelectric cells, which are used in all kinds of devices, from solar panels to digital cameras. The photoelectric effect shattered classical physics and demonstrated that light behaves in ways previously believed impossible. It demonstrated that reality at minimum scales does not follow everyday intuition, but is governed by quantum rules, according to which energy moves in packets and light is both a wave and particle. Dimensional analysis. Imagine trying to check if a bridge will withstand the pressure or if an equation that describes movement makes sense in physics. A tool guarantees coherence between the calculations. Dimensional analysis. It is a method that helps verify equations, convert units, and even derive new physical relationships by examining the fundamental dimensions of physical quantities. Every physical quantity can be broken down into basic dimensions: mass, length, time, temperature, electric current, amount of substance, and luminous intensity. These dimensions form the basis for all physical equations. For example, velocity has dimensions of length per unit time, while force is expressed as mass times acceleration. Dimensional analysis ensures that equations are consistent. If the left and right sides of an equation do not match in terms of fundamental dimensions, the equation is incorrect. That is why you cannot add velocity to energy, because their dimensions are fundamentally different. This method also helps with unit conversions. If a car travels at 60 kilometers per hour and you need the speed in m/second, dimensional analysis ensures that multiplying by the correct conversion factors maintains consistency. Another powerful use is in deriving relationships. Even if the exact equation is unknown, dimensional analysis can suggest possible forms for equations. For example, by analyzing the period of a simple pendulum, it is concluded that it depends on the square root of the length divided by gravitational acceleration. By simply examining the dimensions, Dimensional analysis acts as a safeguard against mathematical errors and provides information on how physical quantities relate. Whether to check an equation, convert units, or discover patterns, it remains an essential tool in physics to ensure that calculations conform to the fundamental principles governing scaling laws. The laws of scale govern how physical properties change when the size of an object is altered, whether in engineering, biology, or physics. These principles determine how structures hold together, how animals work, and how forces interact on different scales. They reveal why a tiny insect can survive a fall from a great height, while a larger animal cannot, and why structures must be designed differently depending on their size. At the core of the laws of scale is geometric similarity. When an object is enlarged or reduced, its length, surface, and volume do not increase at the same rate. If the length of an object is doubled, its surface is multiplied by 4, while its volume is multiplied by 8. This explains why larger animals need proportionally thicker bones to support their weight. Mass increases more rapidly than bone strength. In fluid dynamics, the principles of similarity help to predict how systems of different sizes behave under similar conditions. The Reynolds number, for example, determines whether the flow of a fluid is smooth or turbulent, regardless of whether it is a laboratory experiment or a real-scale airplane. Engineers use this principle to test scale models before building real structures, ensuring accurate predictions. The laws of scale extend beyond mechanics. In thermal physics, heat dissipation depends on the surface area, so smaller objects cool more quickly than larger ones. In electromagnetism, circuits behave differently depending on their scale, influencing everything from microchips to electrical networks. By understanding the laws of scale and similarity, scientists and engineers can predict how structures, organisms, and systems behave when size changes. These principles shape the natural world and the technology around us, ensuring that designs, whether biological or artificial, function efficiently on different scales. Nonlinear dynamics. Not all systems behave predictably or simply. Some evolve very sensitively to initial conditions, where small changes lead to drastically different results. This is the world of nonlinear dynamics, where systems defy simple proportionality and exhibit complex, often chaotic behavior. In linear systems, results scale directly with inputs. If the force is doubled, an object moves twice as fast, but in nonlinear systems the relationships are not so simple. A small push can cause a minor change or trigger a chain reaction. Weather patterns, fluid turbulence, and even population growth are governed by nonlinear dynamics. One of the defining characteristics of nonlinear systems is sensitivity to initial conditions, which is famously demonstrated in the butterfly effect, in which a small disturbance, such as the flapping of a butterfly, can alter weather patterns on the other side of the world. This unpredictability is a distinctive feature of chaotic systems that, although deterministic, are virtually impossible to predict long-term. Another characteristic of nonlinear dynamics is self-organization in systems, such as chemical reactions or traffic flow patterns, which arise spontaneously despite the lack of central force governing them. Feedback loops play a crucial role, since effects can reinforce or suppress changes in unexpected ways. Nonlinear dynamics appears everywhere, from electrical circuits to planetary motion. In engineering, understanding these systems helps design stable bridges and airplanes. In medicine, it explains irregular heartbeats and neuronal activity. Although these systems may seem random, there are often underlying patterns that reveal profound insights into how nature and technology work. Beyond simple cause and effect, by studying nonlinear dynamics, physicists discover the underlying order within seemingly chaotic behavior, allowing for improved predictions and control of systems that previously seemed unpredictable. Chaos theory. Small causes can have massive, unpredictable effects. This is the essence of chaos theory, a branch of mathematics and physics that studies how complex systems evolve in ways that appear random, but follow underlying patterns even in deterministic systems, where outcomes are governed by clear rules. Chaos arises when small differences in initial conditions are amplified over time. One of the best-known ideas of chaos theory is the butterfly effect, the concept that a minor disturbance, such as the flapping of a butterfly, could alter weather patterns around the world. This illustrates the sensitivity to initial conditions, where even the slightest change in input data can produce very different results. Chaotic systems are not truly random, but operate within well-defined limits called attractors. An example is the Lorenz attractor, discovered by meteorologist Edward Lorenz while studying climate models. He discovered that rounding a decimal in his data by a seemingly insignificant amount led to totally different weather predictions. This demonstrated that long-term forecasts for chaotic systems are inherently limited. Chaos appears in a wide range of natural and technological systems. It governs fluid turbulence, electrical circuits, planetary motion, and even population dynamics. In medicine, chaotic patterns emerge in heart rhythms, neuronal activity, and the spread of diseases. Engineers and scientists use chaos theory to predict, manage, or even harness chaotic behavior in practical applications. Unlike simple cause and effect relationships, chaos theory reveals that many systems follow unpredictable but structured patterns, although the future of a chaotic system can never be precisely determined. Understanding its behavior allows for better modeling and control. Chaos is not disorder. It is a deeper form of complexity in which apparent randomness masks an intricate underlying order. Special relativity. Nothing in the universe moves faster than light. This simple fact, discovered by Albert Einstein in his theory of special relativity, redefined our understanding of time, space, and motion. Unlike the fixed and absolute space and time of classical physics, Einstein revealed that these are not rigid and immutable, but flexible, interconnected, and relative. The key idea behind special relativity is that the laws of physics are the same for all observers in uniform motion, no matter how fast they move. If you travel in a spaceship at constant speed, the same physical rules apply to that as to someone standing on Earth. But here's the twist. If you observe someone moving at high speed relative to you, strange things begin to happen. One of the most famous effects is time dilation. When an object moves close to the speed of light, time for that object slows down relative to a stationary observer. If astronauts traveled at a speed close to that of light and returned to Earth, they would have aged much less than those who stayed behind. Another effect is the contraction of a length, where the objects that move at extreme speeds seem shorter in the direction of their movement. Einstein's equations also reveal the equivalence between mass and energy, expressed by the famous equation E equals mc squared. This showed that energy and mass are interchangeable, explaining why nuclear reactions release enormous amounts of energy. Special relativity is not only theoretical, but it supports technologies such as GPS satellites, which must take into account the dilation of time to provide precise location data. It also laid the foundation for general relativity, in which Einstein expanded these ideas to explain gravity's effect on space and time, reimagining movement. Special relativity broke old assumptions and revealed a universe where time, space, and energy are deeply connected. The equivalence between mass and energy. Mass and energy are not separate entities, but are interchangeable. This principle, known as the equivalence between mass and energy, reveals that mass can be transformed into energy and vice versa, fundamentally redefining our understanding of the universe. Einstein's equation, E equals mc squared, states that even a small amount of mass can be converted into an enormous amount of energy. This is because the speed of light, c, is an enormous number, and when it is raised to the square, it drastically magnifies the energy produced. This principle explains why nuclear reactions, in which small amounts of matter are transformed into energy, can power stars or unleash the force of atomic bombs. In daily life, the conversion of mass into energy is not perceptible because most objects do not undergo such transformations. However, it operates constantly at the atomic level in the Sun, where nuclear fusion fuses hydrogen into helium, releasing energy that powers our planet. Particle accelerators collide subatomic particles with each other briefly, converting energy into new particles with mass, which demonstrates that energy in itself can manifest as mass in the appropriate conditions. The equivalence of mass and energy also play a role in modern technology. Positron emission tomography, PET, in medicine is based on the annihilation of tiny particles that convert mass into detectable energy. Even nuclear power plants generate electricity by applying this principle to controlled reactions. This discovery redefined physics, linking matter and energy in a way previously believed impossible, and laid the foundations of nuclear science, quantum mechanics, and modern cosmology, demonstrating that, at its most fundamental level, the universe is a continuous interaction of mass and energy that transforms fluidly and governs the cosmos. General relativity. Gravity is not only a force, but the curvature of space and time itself. This is the basis of general relativity, Albert Einstein's revolutionary theory that redefined our understanding of gravity. Unlike Newton's classical view, according to which gravity is a force that attracts objects, Einstein demonstrated that gravity arises from the curvature of space-time caused by massive objects. Let's imagine that we place a heavy ball on a stretched rubber sheet. The sheet curves, creating a depression. Now, if we roll a smaller ball across the surface, it will not move in a straight line, but curve around a larger ball, just as planets orbit the sun. This curvature of space-time explains why objects follow curved trajectories under the influence of gravity. One of the key predictions of general relativity is gravitational time dilation, the idea that time moves more slowly in stronger gravitational fields. Clocks on the Earth's surface tick slightly slower than those on a satellite in orbit. This effect is real and measurable, and essential for GPS satellites to function precisely. Another consequence is gravitational waves, undulations in space-time produced by accelerating massive objects, such as merging black holes. These waves were detected for the first time in 2015, which confirmed another prediction of the theory of Einstein. Perhaps the most extreme prediction of general relativity is the black hole, a region where gravity is so strong that nothing, not even light, can escape. The existence of black holes, previously theoretical, has now been confirmed by astronomical observations. Einstein's theory transformed physics, explaining everything from planetary motion to the structure of the universe itself. It continues to be one of science's most successful theories, continuously tested and confirmed through experiments and observations, demonstrating that space and time are not fixed, but dynamic, molded by the presence of mass and energy. Quantization in daily life. We think of things as continuous. You can pour water smoothly into a glass, gradually increase the volume of music, or move at any speed you want, but at the smallest scales of reality, nature does not work like that. It operates in discrete steps, a fundamental concept known as quantization. Quantization means that certain physical properties, such as energy, charge, and angular momentum, can only exist in specific and indivisible quantities. This idea revolutionized physics, challenging the classical assumption that everything varies continuously. Instead, many properties behave like a staircase instead of a ramp. Only certain steps are allowed, with no intermediate values. A clear example is the energy levels in atoms. Electrons do not orbit the nucleus at any distance, but exist in specific energy levels, like steps on a staircase. When an electron jumps between these levels, it must absorb or emit an exact amount of energy, so atoms produce distinct spectral lines instead of a continuous rainbow. Quantization is also evident in electrical charge. The charge of a single electron is the smallest possible unit, meaning that all charges in the universe are whole multiples of this fundamental value. There is no such thing as half of an electron's charge. Perhaps the most famous principle of quantization comes from Max Planck's discovery that energy itself is quantized at the microscopic level. Light, which was previously believed to be purely a wave, that is composed of discrete packets called photons, each of which carries a fixed quantity of energy depending on its frequency. Quantization is what distinguishes quantum mechanics from classical physics. It governs the behavior of atoms, semiconductors, and even the fundamental forces of nature, defining the very limits of how energy and matter interact. Wave-particle duality. Light moves like a wave that propagates and interferes with itself. But if that same light is projected onto a metallic surface, it behaves like a stream of particles that release electrons. This paradox is at the heart of wave-particle duality, one of quantum mechanics' most fundamental mysteries. For centuries, physicists have debated the true nature of light. In the 17th century, Isaac Newton described light as a flow of tiny particles, while Christian Huygens argued that it behaved like a wave. The debate seemed settled in the 19th century, when the famous double-slit experiment by Thomas Young showed that light creates an interference pattern, a distinctive feature of waves. But then came the photoelectric effect, in which electrons were emitted when illuminating a metallic surface. Albert Einstein explained this phenomenon using quantized packets of light, or photons, demonstrating that light also behaved like a particle. This discovery earned him the Nobel Prize and shattered the classical understanding of physics. The mystery deepened with quantum experiments with electrons and even with large molecules, which showed that they also exhibit wave-particle duality. When they're not observed, they interfere like waves, but the moment in which they are measured, they behave like particles, as if the observation itself forced them to choose a nature. This duality is not only a peculiarity of light and electrons, but applies to all quantum particles that form the basis of quantum mechanics. It explains phenomena, such as electron orbitals, where electrons do not move in fixed trajectories, but exist as probability waves. Wave-particle duality challenges classical intuition, revealing that reality is not as simple as it seems. The same entity can exhibit two apparently contradictory behaviors, depending on how we observe it. It is a principle that has redefined physics and has given rise to modern quantum theory and revolutionary technologies. Uncertainty principle. You cannot know exactly where a particle is and how fast it is moving at the same time. This is not a limitation of our instruments, but a fundamental property of reality itself. This is the Heisenberg uncertainty principle, one of the central ideas of quantum mechanics proposed by Werner Heisenberg in 1927. The uncertainty principle states that the more precisely we measure the position of a particle, the less precise the measurement of its momentum will be, which is its mass multiplied by its velocity. Conversely, if we determine its momentum, its position becomes uncertain. This is not just an experimental difficulty, but an inherent characteristic of the quantum world. A useful analogy is trying to take a sharp photo of a moving object. If the shutter speed is slow, the object comes out blurry, making it difficult to know exactly where it is. If the shutter speed is fast, a clear position is obtained, but information about the speed at which it was moving is lost. In the quantum world, this blur is not due to technological limitations, but is an intrinsic part of nature. At the heart of this uncertainty lies wave-particle duality. Particles at the quantum scale, such as electrons, behave as both waves and particles. The more we try to confine the position of an electron, the more its wave nature forces its momentum to spread unpredictably. This principle has profound implications. It defines quantum mechanics, which determines how electrons behave in atoms and why particles never have precise classical trajectories. It is also the reason why quantum systems must be described using probabilities instead of exact values. The uncertainty principle is not a defect of physics. It is why the quantum world works as it does, governing everything from semiconductor technology to the structure of atoms themselves. Quantum mechanics, on the smallest scales of reality, changes the rules of physics. Particles no longer behave like small predictable objects, but exist in strange probabilistic states. This is the basis of quantum mechanics, the branch of physics that governs the behavior of matter and energy at the atomic and subatomic level. One of its most famous principles is wave-particle duality. Light, which was previously believed to be purely a wave, can also behave as discrete particles called photons. Similarly, Electrons, which are normally considered particles, can propagate as waves and interfere with each other, as demonstrated in the double-slit experiment. When electrons are fired toward two slits, they do not only pass through one or the other, but create an interference pattern, behaving like waves until they are observed. The mere act of measuring them forces them to adopt a defined state. This is related to another key concept, superposition. Unlike classical objects, quantum particles do not have fixed properties until they are measured. An electron, for example, can exist in multiple energy states at once, collapsing into a single state when observed. This idea extends to quantum computing, where qubits can exist in multiple states simultaneously, greatly increasing computational power. Then there is quantum entanglement, in which two particles are linked no matter how far apart they are. A change in one instantaneously affects the other, apparently violating classical notions of space and time. Einstein called this spooky action at a distance. Quantum mechanics underpins modern technology, from lasers and semiconductors to quantum encryption, but it is still full of unanswered questions that challenge our understanding of reality itself. It is a world in which certainty gives way to probability, where particles defy classical intuition, and where the fundamental nature of existence is still being explored. Quantum entanglement. Two particles separated by great distances remain mysteriously connected. If one is changed, the other responds instantaneously, no matter how far apart they are. This is quantum entanglement, one of the most puzzling and counterintuitive phenomena in physics. At the quantum level, particles do not behave like small billiard balls that follow predictable trajectories, but exist in a superposition of states, which means that their properties remain undefined until they are measured. But when two particles become entangled, their states become linked, no matter how far they travel. Measuring one instantaneously determines the state of the other. Imagine flipping two coins, but instead of falling randomly, they always match, whether heads or tails, even if one is on Earth and the other is on the moon. This defies classical logic. In the early 20th century, Einstein called it spooky action at a distance, because it seemed to violate the idea that information cannot travel faster than light. But experiments have confirmed that entanglement is real and plays a crucial role in modern quantum mechanics. Entanglement has profound implications. It challenges our understanding of space and time, suggesting that quantum information does not behave like ordinary signals. It also forms the basis of quantum computing, where entangled qubits perform complex calculations far beyond classical computers. In quantum cryptography, entanglement guarantees ultra-secure communication, since any attempt to interfere with the system interrupts it. While physicists continue to debate all its implications, entanglement remains one of the most surprising demonstrations of the unpredictability of the quantum world. It is a phenomenon that defies intuition, but drives cutting-edge advances in science and technology, expanding the limits of our knowledge about the universe. Quantum decoherence explains why the strange rules of quantum mechanics do not seem to apply in our everyday world. At the quantum level, particles exist in superposition, meaning they can be in multiple states at once, but in the macroscopic world, objects have defined positions and behaviors. What happens between them? That's where decoherence comes in. In quantum mechanics, particles are described by wave functions, mathematical expressions encoding all possible states of a system. While a system remains isolated from its environment, these wave functions maintain their delicate superposition, but the real world is not isolated. Each particle interacts constantly with its environment. The moment a quantum system interacts with its environment, whether through air molecules, radiation, or even the measurement process, it loses coherence, the wave function collapses, and instead of existing in multiple states, the system stabilizes into a single defined state. Think of it as waves on a calm pond. If there are no disturbances, the waves maintain a smooth and predictable pattern. But if we throw a handful of pebbles, the water becomes chaotic and the waves lose their shape. Decoherence works similarly. It is the interference caused by interactions that alters a quantum system's ability to remain in superposition. This process does not mean that quantum mechanics stops working, but explains why classical reality emerges from the quantum world. Without decoherence, the everyday world would behave like Schrödinger's cat. Objects would not have fixed states until observed. Decoherence is a challenge in quantum computing. Quantum bits or qubits depend on superposition to perform complex calculations, but environmental interference can cause decoherence and erase information. Understanding and controlling decoherence is crucial for advancing quantum technology and unlocking the full potential of quantum mechanics. Renormalization is a powerful mathematical technique that helps make sense of infinite quantities in quantum field theory. Without it, many equations in physics would fall apart, giving meaningless results instead of meaningful predictions. At the quantum level, particles not only interact directly, but constantly emit and absorb virtual particles, creating a sea of fluctuations. These interactions, when calculated naively, give rise to infinite values. For example, the charge of an electron or the mass of a particle might appear infinite, rendering the equations meaningless. Renormalization solves this by introducing a systematic way to handle infinities instead of treating them as infinite as physicists, but redefine the fundamental parameters, such as mass and charge, so that only the measurable finite quantities remain. It's like adjusting the zoom of a camera to different scales. Details change, but the overall image remains consistent. One of the most famous applications of renormalization is quantum electrodynamics, QED, the theory describing how light and charged particles interact. Initially, the QED equations predicted infinite results for observable properties, but renormalization corrected these infinities, producing calculations that matched experiments with astonishing precision. Beyond QED, renormalization plays a role in quantum chromodynamics, QCD, the theory of strong nuclear forces, and even in condensed matter physics, helping explain phase transitions in materials. The idea extends to understanding how physical laws change at different energy scales, revealing deeper connections between the forces of nature. Quantum field theory. Everything around you, from the screen you're looking at to the air you breathe, is made of particles. But what if particles are not the fundamental building blocks of reality? Quantum field theory, QFT, reveals that what we call particles are just excitations in invisible fields extending throughout the universe. In classical physics, particles are seen as small solid objects moving through space, but in QFT, the universe is described as a collection of quantum fields, one for each fundamental force and type of particle. These fields are like an ocean, and the particles are the waves that arise when energy disturbs the surface. For example, an electron is not an isolated tiny object, but a localized disturbance in the electron field. QFT combines the principles of quantum mechanics and special relativity to explain how particles appear, interact, and disappear. One of its greatest successes is the description of the electromagnetic field through quantum electrodynamics, QED, explaining how light and charged particles interact. This framework is incredibly accurate. Its predictions match experiments with a precision of 1 part in a billion. QFT also underlies the standard model of particle physics, unifying 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It predicts the existence of particles such as the Higgs boson, which was experimentally confirmed in 2012, demonstrating how particles acquire mass. In essence, quantum field theory redefines our understanding of existence, not as a collection of tiny objects, but as a universe woven from fundamental fields. Although one of the most successful theories in physics, it remains incomplete and leaves unanswered questions about gravity, dark matter, and the nature of space-time itself.